Across the endless stretch of the universe, galaxies are scattered in every direction, far beyond what the eye can imagine. There are billions of galaxies, and each one is a massive world of its own. Inside them exist countless stars, hidden planets, and strange phenomena we are only beginning to understand. These galaxies are filled with enormous systems of stars, gigantic clouds of glowing gas, and powerful regions where new stars are being born, places so extreme and vast that nothing on Earth truly compares. But how did we get the galaxies wrong for so long? From the centre of the Milky Way to the farthest parts of space, we'll explore how these huge structures are created and change over time, look at clear images of galaxies taken from very far away and from different periods in the universe, and uncover important new findings within our own galaxy. I'm fascinated by the idea of us all watching this from our tiny corner of the universe. Let me know in the comments what time it is where you are and whether you're watching this under sunlight or starlight. And if you're ready for the voyage, hitting that like button and subscribing tells me you're on board. The Milky Way galaxy is the huge island of stars that holds our solar system. Its name comes from how it looks from Earth, a soft, blurry band of light stretching across the night sky. This glow comes from countless distant stars that are so far away we cannot see them one by one with our eyes. The Milky Way is a barred spiral galaxy, which means it has spiral arms that curve out from a bright central bar. It spreads about 87,400 light-years across, and is about 1,000 light-years thick in the spiral arms, getting much thicker near the central bulge. Some computer models suggest that its outer areas, which include dark matter and scattered stars, may reach as far as 2 million light-years in diameter, a size that makes our galaxy truly enormous. The Milky Way is not alone in space. It has many smaller companion galaxies, like the Large and Small Magellanic Clouds, and together they form part of a bigger group called the Local Group. This group is part of an even larger structure called the Virgo supercluster, which itself is part of a huge cosmic network known as the Laniakea supercluster, a giant area of connected galaxies that stretches across hundreds of millions of light-years. Our galaxy has between 100 billion and 400 billion stars, and possibly a similar number of planets. The solar system is about 27,000 light-years from the centre of the Milky Way, on the inner edge of one of its spiral arms called the Orion Arm. Closer to the centre, within about 10,000 light-years, stars gather tightly to form a bright bulge. At the very centre of the Milky Way is a mysterious and powerful object, Sagittarius, a star, a supermassive black hole with a mass about 4 million times that of the Sun. Some of the oldest stars in the Milky Way are almost as old as the universe itself, having formed not long after the Dark Ages following the Big Bang. These ancient stars act as silent witnesses to the earliest chapters of cosmic history. The Milky Way first showed its true nature through the work of Galileo Galilei in 1610, when he used his telescope to show that the blurry band of light was made of countless stars. For centuries after, astronomers thought the Milky Way held every star in existence. It was not until the Great Debate of 1920, between Harlow Shapley and Heber Doost Curtis, and later observations by Edwin Hubble in 1923, that scientists realized the Milky Way is just one of many galaxies spread across the vast universe. When seen from a dark place, the Milky Way looks like a pale, glowing arc, about 30 degrees wide, stretching across the night sky. Every star we can see without a telescope belongs to the Milky Way, but the name Milky Way refers specifically to this bright band of light. Its glow comes from the combined light of countless stars and space dust, concentrated along the galaxy's plane. Some areas of the band shine more and look like soft patches called star clouds, the largest being the Large Sagittarius star cloud, part of the galaxy's central bulge. In contrast, the dark gaps that break the band, like the Great Rift and the Coalsack Nebula, are caused by thick clouds of space dust that block the light of stars behind them. People in the southern hemisphere, including the Inca and Australian Aboriginals, once saw these dark patches not as empty space, but as dark cloud shapes, figures outlined by the darkness. The part of the sky where the Milky Way blocks the view of more distant galaxies is called the zone of avoidance. Despite its size, the Milky Way has a low surface brightness, which means it can easily be hidden by background light like moonlight or city lights. To see it clearly, the sky must be darker than 20.2 magnitude per square arc second, a level rarely reached in modern cities. If the night is dark enough for stars of magnitude plus 5.1 or brighter to be seen, the Milky Way becomes visible, and under even darker skies, with stars visible down to plus 6.1, its fine details appear beautifully. Unfortunately, because of light pollution, more than 1/3 of the world's people can no longer see the Milky Way from where they live. From Earth, the Milky Way's glowing plane passes through 30 constellations. Its centre is in the direction of Sagittarius, where it shines the brightest. From there, the band stretches around the sky toward Auriga, opposite the galactic centre, and then loops back to Sagittarius, dividing the sky into two almost equal halves. The galaxy's plane is tilted by about 60 degrees relative to the ecliptic, the sun's path through the sky, and by about 63 degrees relative to the celestial equator. This angle gives the Milky Way its sweeping, graceful arch across the sky, a breathtaking sight that connects everyone on Earth to the giant structure of the galaxy we call home. Long before telescopes showed the true structure of our galaxy, ancient thinkers tried to explain the mysterious pale band that stretches across the night sky. In his famous work Meteorologica, written in the 4th century before Christ, the Greek philosopher Aristotle described earlier ideas by his predecessors Anaxagoras and Democritus. These early philosophers, who lived between the 5th and 4th centuries before Christ, thought the Milky Way was a faint glow made by distant stars hidden behind the Earth's shadow. They believed that while some stars got their light from the sun, others shone too dimly to be seen clearly, because their light was drowned out by the sun's brightness. Aristotle, however, had a different idea. He thought the Milky Way was not far away in space, but part of the upper layer of Earth's atmosphere. He believed it was made from fiery vapours and sparks left behind by stars burning in the sky, which created a glowing circle around the heavens. In his explanation, the pale, milky look of the band came from light being bent and scattered by the atmosphere itself. Many centuries later, in the 6th century after Christ, the philosopher Olympiodorus the Younger disagreed with Aristotle. He said that if the Milky Way really existed in Earth's atmosphere, its appearance should change depending on where you were or the time of night. Since it always looked the same from anywhere on Earth and did not move like nearby objects, he argued it must be part of the sky far beyond the moon. This idea of the Milky Way being part of the heavens, not the atmosphere, became very important in later centuries, especially among Muslim scholars. In the 10th and 11th centuries after Christ, the Persian astronomer al-Biruni described the Milky Way as a huge collection of countless pieces of fuzzy stars. Not long after, in the early 12th century, the Andalusian astronomer Ibn Parsay suggested that the Milky Way was actually made of many tiny stars so close together that they looked like a continuous bright band in the sky. He even used his observation of Jupiter and Mars passing close together around the years 1106 or 1107 as proof. Another Persian astronomer, Nasir al-Din al-Tusi, who lived in the 13th century, described the Milky Way in his book Tadhkira as a huge group of very small stars packed closely. Because the stars were so many and so close, they looked like pale clouds, which explained why their light looked milky. Later, the scholar Ibn Qayyim al-Jawziyah, writing in the 14th century, shared the same idea. He described the Milky Way as a countless number of tiny stars packed together in the sphere of fixed stars. The first clear proof that the Milky Way was really made of stars came much later, in 1610. Using one of the earliest telescopes, Galileo Galilei looked closely at the Milky Way and found that it was made of an enormous number of faint stars packed so close that their light blended together. He concluded that its blurry look was not from Earth's atmosphere, as Aristotle thought, but from the combined glow of countless distant suns. More than 100 years later, in 1755, the thinker Immanuel Kant built on earlier ideas suggested by the astronomer Thomas Wright. Kant said that the Milky Way was a huge spinning disk, made of billions of stars held together by gravity, just like the planets of the solar system move around the sun, but on a much larger scale. He also suggested that the faint cloudy patches in the sky might actually be other island universes, or galaxies, far beyond our own. This term, island universes, stayed popular well into the early 1900s. In 1785, the astronomer William Herschel made the first serious effort to map the shape of the Milky Way. By carefully counting the stars in different parts of the sky, He made a diagram showing the Milky Way as a flattened disk with the solar system near its centre. 60 years later, in 1845, Lord Rosse built a strong new telescope that let him see details in faraway nebulae. He was the first to tell the difference between those that were oval-shaped and those that were spiral-shaped. In some of these nebulae, he could even see individual stars, giving strong support to Kant's earlier idea that such nebulae might actually be other galaxies. By the early 1900s, astronomers were starting to realise that the Milky Way was not just a random group of stars. In 1904, the Dutch astronomer Jacobus Kapteyn studied how stars moved and noticed that they could be grouped into two large streams moving in opposite directions. His findings gave the first signs that the Milky Way was rotating as a whole, a discovery later confirmed by astronomers Bertil Lindblad and Jan Oort. In 1917, the American astronomer Heber Doost Curtis studied a bright nova that appeared in the Great Andromeda Nebula, now called the Andromeda Galaxy. By comparing it with other novae seen in photographs, he realised that these objects were much dimmer than those found within the Milky Way. From this, he estimated that Andromeda was about 150,000 parsecs away, far beyond the edges of our galaxy. Curtis became a strong supporter of the island universe idea, saying that spiral nebulae were actually separate galaxies. In 1920, the famous Great Debate happened between Harlow Shapley and Heber Curtis. They argued about the true size of the Milky Way and whether spiral nebulae like Andromeda were part of it or separate galaxies. Curtis supported the idea of separate galaxies, pointing out that Andromeda had dark dust lanes like those in the Milky Way, and that its light showed a clear Doppler shift, showing it was very far away. The debate was finally settled in the early 1920s by Edwin Hubble, using the strong 2.5 metre, 100-inch Hooker telescope at the Mount Wilson Observatory. Hubble was able to photograph spiral nebulae in amazing detail. He could see their outer parts as individual stars and identified Cepheid variable stars, whose brightness allowed him to measure their distances accurately. Hubble found that the Andromeda Nebula was about 275,000 parsecs from the Sun, far too far to be part of the Milky Way. This discovery proved beyond doubt that the universe was much larger than anyone had imagined, and that the Milky Way was just one of countless galaxies spread across space. The European Space Agency's spacecraft Gaia is one of the most remarkable missions in modern astronomy. Its main goal is to measure distances to stars by carefully watching their tiny shifts in position, called parallax. Using this method, Gaia has been able to estimate the positions and distances of over 1 billion stars, making the most detailed and accurate map of our Milky Way ever made. Scientists often call Gaia's data transformational because it has completely changed how we understand the structure, movement and development of our galaxy. Before Gaia, astronomers had reliable data for only about 2 million stars back in the 1990s. Thanks to this mission, that number has now grown to an amazing 2 billion stars. The area of space that can now be measured has increased by 100 times in radius, and the accuracy of these measurements has improved by about 1,000 times, letting scientists see our cosmic neighbourhood more clearly than ever. In 2020, a major study found something extraordinary. Gaia had detected a slight wobbling motion of the Milky Way itself. Astronomers think this movement might be caused by several factors. Maybe the galaxy's disk is slightly tilted compared to its outer halo, or maybe it is being affected by material that fell into it long ago, or even by the pull of nearby smaller galaxies. In April 2024, scientists released the first maps showing the Milky Way's magnetic fields, also made using Gaia's precise observations. Our Sun sits near the inner edge of a spiral arm called the Orion Arm, inside a region of gas and dust called the local fluff, which itself is inside a larger cavity of hot gas called the local bubble. This area lies between two large structures called the Radcliffe Wave and the Split Linear Structure, which were once thought to be part of a ring called the Gould Belt. Astronomical studies have also helped find out how far the Sun is from the very centre of the Milky Way, where a giant black hole called Sagittarius A star is located. According to calculations by astronomer Reinhard Genzel and his team in 2016, the Sun is about 27,140 light-years from the galactic centre. Another study from the same year, led by Andrea Ghez's team, found a slightly smaller distance of about 25,640 light-years. The The Sun is also roughly between 16 and 98 light-years above the central plane of the galaxy's disk. The gap between our spiral arm and the next one outward, called the Perseus arm, is around 6,500 light-years. Interestingly, our solar system lies in what scientists call the Milky Way's galactic habitable zone. A region thought to have conditions good for life. Near the Sun, there are about 208 stars brighter than absolute magnitude 8.5 within 49 light-years. That means there is roughly one bright star for every 2,360 cubic light-years. But when all stars are counted, including the dim ones, there are 64 known stars within 16 light-years of the Sun, not counting 4 brown dwarfs. This shows a much higher density, about one star for every 284 cubic light-years. This difference shows that dim stars far outnumber bright ones. Across the sky, there are only about 500 stars visible to the naked eye brighter than magnitude 4, but more than 15.5 million that are brighter than magnitude 14 and can be seen through telescopes. The Sun itself is not still. It moves through space, travelling in a general direction called the solar apex, which points toward the bright star Deneb in the constellation Cygnus, almost at a right angle to the direction of the galactic centre. The Sun's path around the Milky Way is roughly oval, but its orbit is slightly disturbed by the galaxy's spiral arms and the uneven spread of mass in the galactic disk. During each orbit, the Sun moves up and down through the galactic plane about 2 to 3 times, in a motion a bit like a swinging pendulum. For many years, some scientists thought these swings might be linked to mass extinction events on Earth, but more recent studies have shown no clear connection. It takes our solar system about 240 million years to complete one full orbit around the Milky Way, sometimes called a galactic year. Since the Sun was born about 4.5 billion years ago, it has completed between 18 and 20 such orbits, and only a tiny part, about 1/12 of a thousandth, of a single orbit has passed since humans first appeared on Earth. The solar system moves around the galaxy's centre at about 220 kilometers per second, or roughly 490,000 miles per hour, which is just a tiny fraction, about 0.07% of the speed of light. Through the surrounding interstellar material of the heliosphere, the Sun travels at about 84,000 kilometers per hour. At this speed, it would take about 1,400 years for the solar system to move a distance equal to 1 light-year, or about 8 days to travel 1 astronomical unit, the average distance between the Earth and the Sun. Today, our solar system is moving in the direction of the constellation Scorpius, following the plane of the ecliptic, continuing its endless and smooth journey through the huge and shining spiral of the Milky Way. The Milky Way galaxy is divided into 4 main sections called galactic quadrants. These quadrants are like 4 slices of a large circular disk, and they help astronomers describe where stars, nebulae, and other cosmic objects are located in our galaxy. To organise this huge system, scientists use something called the Galactic Coordinate System, a kind of space map that puts the Sun at the very centre. From this point, the sky is divided into 4 numbered regions, the 1st, 2nd, 3rd, and 4th galactic quadrants, each covering a quarter of the Milky Way's circular shape. When seen from above the northern side of the Milky Way, from a position high above the galactic centre, the angle called galactic longitude increases in a counterclockwise direction, starting from 0 degrees at the line going from the Sun through the centre of the galaxy. If, however, someone could look at the galaxy from far below its southern side, that same angle would seem to increase in the opposite, clockwise direction. From these different views, the spinning and structure of our galaxy can be better understood. The Milky Way itself is one of the 2 biggest galaxies in our local cosmic neighbourhood, called the Local Group, which also includes the large Andromeda galaxy. However, astronomers still do not fully know how far the Milky Way's visible disk reaches, or exactly how its edges are defined. Most of the galaxy's stars are found within a diameter of about 26 kiloparsecs, which is roughly 80,000 light-years. Beyond this area, the number of stars drops sharply, leaving only a few scattered stars in the farthest parts of the galactic disk. Measuring the size of a galaxy is not easy. Astronomers use several methods, and each one can give a slightly different answer. The most widely used standard is called D25, which marks the edge of a galaxy based on how its brightness fades toward the edges. Specifically, this point is where the galaxy's brightness in blue light, around a wavelength of 445 nanometers, becomes faint enough to reach a value of 25 magnitudes per square arc second. In 1997, astronomer Peter Goodwin and his team compared the brightness of certain stars called Cepheid variables in 17 other spiral galaxies to those in the Milky Way. By looking at these data, they estimated our galaxy's visible diameter to be about 26.8 kiloparsecs, or roughly 87,400 light-years. They based this on a model in which the Milky Way's disk has an exponential shape, with a central brightness of about 22.1 blue magnitudes per square arc second, and a disk scale length of around 5 kiloparsecs, equal to 16,300 light-years. This result shows that the Milky Way is a little smaller than the Andromeda Galaxy, and slightly below the average size of other spiral galaxies, which are around 28 kiloparsecs wide, or about 92,000 light-years. This means that, contrary to earlier beliefs, our galaxy and Andromeda are not huge among spirals, but rather quite normal in size. To imagine this, if the solar system, reaching out to Neptune, were the size of a US quarter coin, a bit less than 1 inch across, the Milky Way would stretch roughly across the entire width of the continental United States. An older study from 1978 gave a smaller estimate for the galaxy's diameter, about 23 kiloparsecs, or 75,000 light-years. In 2015, astronomers discovered a large ring-shaped group of stars called the Triangulum Andromeda Ring, also known as the Triand Ring, which seems to ripple above and below the otherwise flat plane of the Milky Way. Together with another structure called the Monoceros Ring, this ring may be part of the galaxy's extended outer disk, possibly reaching a diameter of at least 50 kiloparsecs, or about 160,000 light-years. However, a later study in 2018 suggested a different explanation, that these rings might actually be stars that were once part of the main disk, but were thrown out by gravity, forming what astronomers call stellar overdensities. Another study, also published in 2018, found signs that the Milky Way's disk may go even farther than previously thought, perhaps as far as 31.5 kiloparsecs, or about 103,000 light-years from the galactic center. This was surprising, since earlier research suggested that the galaxy's star-filled region ended at around 20 kiloparsecs, or 70,000 light-years. Even more surprising results came in 2020, when astronomers estimated the edge of the Milky Way's dark matter halo, the invisible sphere of mysterious material surrounding the galaxy, to be about 292 kiloparsecs, or roughly 952,000 light-years from the center. This means the whole dark matter halo could stretch nearly 1,900,000 light-years across. The Milky Way's main stellar disk, where most of its stars, gas clouds and planetary systems are, is estimated to be about 1 1/3 kiloparsecs thick, which equals roughly 4,000 light-years. The Milky Way galaxy is a huge system whose total mass is estimated to be about 880 billion times the mass of the Sun, measured up to a distance of about 200,000 light-years from its center. However, astronomers do not all agree on the exact number, because different methods and observations give slightly different results. Some studies suggest that the Milky Way might weigh as little as 580 billion solar masses, which would make it a little smaller than our neighbouring Andromeda Galaxy. In the year 2009, measurements using a network of radio telescopes called the Very Long Baseline Array showed that some stars near the outer edge of our galaxy move at speeds as high as 254 kilometers per second, which is about 570,000 miles per hour. Because a star's orbit speed depends on the total mass inside its orbit, these results suggested that the Milky Way might be much heavier than previously thought, possibly as heavy as Andromeda, with around 700 billion solar masses within about 160,000 light-years of its center. The following year, in 2010, another measurement based on the movement of stars in the galactic halo found a similar number, estimating 700 billion solar masses within about 80,000 light-years. A few years later, in 2014, new studies placed the total mass of the Milky Way at around 850 billion solar masses, which is roughly half that of the Andromeda Galaxy. Then in 2019, astronomers suggested an even higher number, about 1,290 billion solar masses, A large part of the Milky Way's mass is not made of visible stars or gas, but of dark matter, a mysterious and invisible type of matter that pulls with gravity but does not give off light. Scientists think that this dark matter forms a huge, almost spherical halo that stretches more than 100,000 light-years beyond the galactic centre. Models of the Milky Way suggest that this dark matter alone could have a mass of between 1 trillion and 1.5 trillion solar masses. Some studies from 2013 and 2014 offered a wider range, from as low as 800 billion to as high as 4.5 trillion solar masses. By comparison, the total mass of all the stars in the Milky Way is thought to be between 46 billion and 64 billion solar masses. Besides stars, the galaxy also contains large amounts of interstellar gas made up of about 90% hydrogen and 10% helium by weight. About 2/3 of the hydrogen is in atomic form, while the remaining third is in molecular form. The total mass of this gas is roughly 10 to 15% of the mass of all the stars in the galaxy. There is also a small amount of interstellar dust, which makes up about 1% of the gas's total mass. In March of 2019, astronomers said that the virial mass of the Milky Way, a measure that includes all the matter held together by gravity, was about 1,540 billion times the mass of the Sun within a radius of around 130,000 light-years. This was more than twice what earlier studies had found and suggested that almost 90% of the Milky Way's total mass could be dark matter. However, in September of 2023, new data from the Gaia spacecraft gave a much lower estimate, showing a virial mass of only 206 billion times the Sun's mass, about 1/10 of previous measurements. The Milky Way has between 100 billion and 400 billion stars, and it likely has at least as many planets. The exact number is unknown because the smallest and faintest stars are very hard to see, especially those more than 300 light-years from the Sun. In comparison, the nearby Andromeda galaxy may have about 1 trillion stars. Inside our galaxy, astronomers think there are about 10 billion white dwarfs, 1 billion neutron stars, and around 100 million black holes. Between the stars is a wide, thin layer of gas and dust called the interstellar medium. This disk stretches as far as the stars themselves, and its thickness changes, from a few hundred light-years in the colder areas to several thousand light-years in the warmer ones. The Milky Way's disk does not have a clear outer edge. Instead, the number of stars slowly goes down as you move away from the galaxy's centre. Beyond about 40,000 light-years from the centre, the star density drops much faster. Around the main disk is a huge halo of old stars and ancient globular clusters, stretching out until it is limited by the paths of the galaxy's two main smaller companion galaxies, the Large and Small Magellanic Clouds. These small galaxies come as close as 180,000 light-years from the Milky Way centre. If objects in the halo moved beyond this distance, their paths could be disturbed by the gravity of the Magellanic Clouds, possibly throwing them out of the Milky Way. The Milky Way's total brightness in visible light is thought to have an absolute magnitude of about -20.9, making it one of the brighter galaxies in our local group. Observations show that there may be at least one planet for every star in the Milky Way. Some studies even suggest there are more free-floating planets, those not orbiting any star, than there are stars. According to a 2013 study of the five-planet system Kepler-32, the Milky Way probably has between 100 billion and 400 billion planets. Another study from that year estimated that at least 17 billion of those planets are about the size of Earth. Later, in November of 2013, data from the Kepler Space Telescope suggested there could be as many as 40 billion Earth-sized planets orbiting in the habitable zones of stars like the Sun and smaller red dwarfs. About 11 billion of these could be around stars like our Sun. The nearest known Earth-sized planet is thought to be Proxima Centauri b, about 4.2 light-years away, according to a 2016 study. Smaller, rocky planets like Earth seem to be much more common than large gas giants, though they are harder to find because of their small size and faintness. Scientists have also found signs of exocomets, icy bodies orbiting other stars, which may also be common in our galaxy. In November of 2020, researchers estimated that there could be over 300 million potentially habitable planets in the Milky Way alone. Interestingly, compared to more distant galaxies, the Milky Way produces a relatively low number of neutrinos, ghost-like particles that hardly interact with matter, leading astronomers to call our galaxy a neutrino desert. The Milky Way is made up of a bright bar-shaped center surrounded by a huge warped disk of stars, gas and dust. Its shape is like what astronomers call an SBC spiral galaxy, one with loosely wound arms that twist outward from the center. Scientists began thinking in the 1960s that the Milky Way might not be a simple spiral galaxy, but a barred spiral one, meaning its central region is stretched into a long bar shape. This was confirmed in 2005 when the Spitzer Space Telescope showed that the Milky Way's central bar was even bigger than expected. Our Sun is about 25,000 to 28,000 light-years away from the very center of the Milky Way. Astronomers measure this distance using different geometric methods, and by studying special stars called standard candles that help measure space distances more accurately. The inner part of the galaxy, about 10,000 light-years from the center, has a dense group of mostly old stars called the Galactic bulge. Some scientists think the Milky Way may not have a real bulge, but instead a pseudo-bulge formed by the movement of stars in the central bar. Others think what looks like a bulge may just be a peanut-shaped structure caused by gravity within that bar. At the very center of our galaxy is a powerful and mysterious radio source called Sagittarius A star. The movement of gas and stars around it shows the presence of an enormous invisible object, a supermassive black hole estimated to weigh between 4 million and 4.5 million times as much as our Sun. This black hole is fairly quiet, pulling in matter very slowly, only about 100,000th of a Sun's mass per year, which means it is currently inactive compared to the centers of some other galaxies. Observations suggest that almost all large galaxies have such huge black holes at their centers. The exact size and shape of the Milky Way's central bar are still being discussed. Estimates put its half-length between about 3,000 and 16,000 light-years, tilted by roughly 10 to 50 degrees from our line of sight toward the galactic center. Some astronomers even think that our galaxy might have two bars, a smaller one inside a larger one, although this idea is still debated. The bar is thought to be surrounded by a structure called the 5 kiloparsec ring, which contains much of the Milky Way's molecular hydrogen and is one of the most active areas for star formation. If we could see our galaxy from the nearby Andromeda galaxy, this bright ring would stand out as one of the most glowing features of the Milky Way. In June of the year 2023, a research team led by Naoko Kurahashi-Nielsen used a new cascade neutrino detection method to see for the first time neutrinos coming directly from the flat plane of the Milky Way, effectively giving humanity its first ever neutrino picture of our home galaxy. Since the year 1970, several space missions have detected gamma rays with an energy of 511 kilo-electron volts coming from the direction of the galactic center. These rays are made when positrons, which are particles of antimatter, collide and cancel out with electrons. In 2008, scientists discovered that the sources of these gamma rays follow a pattern like that of low-mass X-ray binary systems, pairs of stars where one is a compact, dense object like a neutron star. This finding suggested that such systems might be sending positrons into space, where they meet electrons and disappear in bursts of radiation. The area producing these rays was found to stretch about 10,000 light-years and shine with a brightness roughly equal to 10,000 suns. Then, in 2010, astronomers discovered two huge, balloon-like structures rising above and below the Milky Way's center. Each of these Fermi bubbles, as they were called, stretches about 25,000 light-years across, roughly 1/4 of the galaxy's total width. They reach all the way into the regions of the sky where the constellation Grus and Virgo are. Later observations using the Parkes radio telescope showed that these bubbles are linked to strong magnetized outflows, likely caused by bursts of star formation in the galaxy's central 200 parsecs, or about 640 light-years. On the 5th of January 2015, NASA saw an extraordinary X-ray flare from Sagittarius A star, about 400 times brighter than its normal output. This record-breaking burst might have been caused by a small asteroid being torn apart as it fell into the black hole, or possibly by magnetic field lines snapping and reconnecting in the swirling gas around it. Beyond the central bar, the Milky Way's disk has 4 big spiral arms made of stars, gas and dust. These arms are areas where space material is denser than average, and where many new stars are born inside glowing hydrogen clouds and huge molecular clouds. However, astronomers still do not completely agree on the exact layout of these arms. The Milky Way's spiral shape is not a perfect spiral. Its arms often branch, merge, and twist in complex, uneven ways. The Sun itself seems to be inside a smaller branch of one of these arms, called the local arm, which shows that the galaxy's shape is far from symmetrical. The angle at which the arms curve outward from the centre, called the pitch angle, is thought to range between about 7 and 25 degrees. The Milky Way's spiral structure is much more complex and fascinating than it may look from Earth. Inside the Sun's orbit around the galaxy's centre lie two of its spiral arms, the Scutum Centaurus arm and the Carina Sagittarius arm. These arms are special because they reach what astronomers call tangent points, areas where the line of sight from the Sun runs directly along the length of an arm. If these spiral arms really contain more stars than the average parts of the galactic disk, this difference should be visible by counting the number of stars in those regions. When astronomers looked at these areas using near-infrared light, a type of light that can pass through thick clouds of cosmic dust, they found something remarkable. The Scutum Centaurus arm had about 30% more red giant stars than expected, showing that it is indeed a major stellar arm. However, the same increase was not seen in the Carina Sagittarius arm, suggesting that the Milky Way may have only two large arms full of old stars, the Perseus arm and the Scutum Centaurus arm. The other arms seem to have mostly gas and fewer old stars. Later, in December of the year 2013, astronomers studying young stars and star-forming areas found that these followed a pattern of 4 spiral arms. This means that, while the Milky Way has 2 main arms rich in old stars, it seems to have 4 arms made of gas and young stars. The reason for this puzzling difference between the two observations is still unknown. In the 1950s, astronomers led by Hendrik van Woerden made another important discovery. Using radio waves with a wavelength of 21 centimeters to study atomic hydrogen, they found a structure now called the near 3 kiloparsec arm, sometimes simply the 3 kiloparsec arm. This arm was found moving away from the Milky Way's central bulge at a speed greater than 50 kilometers per second. It lies in the 4th galactic quadrant, roughly 5 2/10 kiloparsecs from the Sun, and about 3 3/10 kiloparsecs from the galactic centre. Decades later, in the year 2008, astronomer Tom Dame discovered another similar feature, the far 3 kiloparsec arm in the 1st galactic quadrant, located about 3 kiloparsecs, or roughly 10,000 light-years, from the galactic centre. A computer simulation published in the year 2011 suggested that the Milky Way's spiral shape might have been formed through repeated collisions with a much smaller galaxy, the Sagittarius Dwarf elliptical galaxy. Some researchers also think that our galaxy might have 2 different spiral patterns, an inner one, formed by the Sagittarius arm, which spins quickly, and an outer one, formed by the Carina and Perseus arms, which spin more slowly and are more tightly wound. This slower outer pattern could create a shape like a ring, sometimes called a pseudo-ring, with the Cygnus arm acting as a bridge between the two systems. Beyond these main spiral arms lies a mysterious feature called the Monoceros ring, or outer ring, a huge loop of gas and stars that may have been pulled from smaller galaxies billions of years ago. However, some scientists now think that this ring is not a separate structure at all, but just a region of the Milky Way's disk where stars are packed more closely because of its bent and flared shape. In fact, the Milky Way's disk itself is not completely flat. It bends and twists into a gentle S shape as it spreads outward. Around this large disk is a roughly round halo filled with ancient stars and dense groups called globular clusters. About 90% of these clusters are found within 100,000 light-years of the galactic centre, though a few, like PAL 4 and AM1, are more than 200,000 light-years away. Interestingly, around 40% of these clusters move in the opposite direction to the Milky Way's overall spin, following looping or rosette-shaped paths rather than smooth oval orbits like planets around stars. While the disk is filled with clouds of dust that block certain kinds of light, the halo is much clearer. New stars are constantly being born within the disk, especially inside the spiral arms where gas and dust are thick, but almost no star formation happens in the halo, where there is very little cool gas left. Groups of young stars called open clusters are also found mainly within the disk. In the early years of the 21st century, astronomers made new discoveries that expanded our knowledge of the Milky Way structure. Observations showed that the disk of the nearby Andromeda galaxy stretches much farther than previously thought, suggesting that our own galaxy's disk might do the same. Evidence for this comes from finding the outer arm extension of the Cygnus arm and another similar extension of the Scutum Centaurus arm. When astronomers found the Sagittarius dwarf elliptical galaxy, they also noticed a long ribbon of stars, leftovers being torn apart by the Milky Way's gravity as this smaller galaxy moves around it. In the year 2004, scientists found another ring-like structure made of star debris, orbiting in the same plane as the Milky Way. At first, this was thought to be the remains of a small system called the Canis Major dwarf galaxy, but later studies suggested it was actually part of the Milky Way's natural bend, an idea supported by more evidence as of the year 2021. The Sloan Digital Sky Survey of the northern sky revealed a huge, faint structure inside our galaxy, covering an area about 5,000 times larger than the full moon. This group of stars rises almost straight up from the plane of the Milky Way's spiral arms, and astronomers believe it could be the remains of another small galaxy merging with ours. This mysterious feature has been tentatively named the Virgo stellar stream and is in the direction of the constellation Virgo, about 30,000 light-years away. High above and beyond the stars of the Milky Way, there exists not only a halo made up of very old stars but also a vast and mysterious ocean of gas. Observations from the Chandra X-ray Observatory, XMM Newton, and the Japanese satellite Suzaku have revealed this hidden glowing halo of hot gas that stretches hundreds of thousands of light-years into space, far beyond the reach of the Milky Way's star-filled edge and almost as far as the large and small Magellanic Clouds. This gas halo is not just an empty mist, it is huge in mass, holding almost as much matter as the entire Milky Way. The temperature of this hot gas is between 1 and 2.5 million kelvins, which is about 1.8 to 4.5 million degrees Fahrenheit. In the earliest times of the universe, when it was only a few billion years old, astronomers have found that there was about 1 part of normal, or baryonic, matter for every 6 parts of dark matter. Yet today, when they look around nearby galaxies like our own, only about half of that normal matter can be found. If it is true that this huge halo of hot gas really weighs as much as the Milky Way, it might finally show where those long-lost baryons have been hiding, floating invisibly around our galaxy all along. Inside the Milky Way, both stars and gas spin around the galactic center in a smooth, complex dance. Unlike the planets of the solar system, which move faster the closer they are to the sun, the stars in the Milky Way move at almost the same speed no matter how far they are from the center. Most of them move at about 200 to 220 kilometers per second, completing huge orbits over millions of years. This nearly constant motion is a mystery because if the galaxy contained only the visible matter we can see, its stars, gas and dust, the speed of rotation should slow down farther from the center, but it doesn't. The flatness of the Milky Way's rotation shows that there must be something else, something invisible, adding to its gravity. This hidden matter, called dark matter, seems to make up most of the galaxy's total mass. A few scientists, however, think that maybe gravity itself works differently on such large scales, but most astronomers agree that dark matter is the best explanation. The Milky Way story began more than 13.5 billion years ago, shortly after the great event known as the Big Bang. Tiny ripples and clumps in the young universe's matter began to grow under the pull of gravity, and some of these dense regions became the seeds of what would one day form globular clusters, spherical groups of very old stars that still hover in the Milky Way's halo today. Over time, nearly half of the matter that now makes up the Milky Way may have come from other galaxies. Within only a few billion years, the growing galaxy spun faster and faster, and as it did, the swirling clouds of gas flattened into a big rotating disk. From this disk, new generations of stars were born, including our own Sun. As time passed, the Milky Way kept growing. It merged with other small galaxies, swallowing them into its spiral body, and even now it continues to pull in its smaller neighbours. 2 of its largest companions, the Large and Small Magellanic Clouds, are slowly being drawn in through long streams of gas called the Magellanic Stream. Even fast-moving clouds like the Smith Cloud are falling toward the Milky Way, adding new material to its halo. Simulations of cosmic history suggest that about 11 billion years ago, the Milky Way went through a big merger with a massive galaxy astronomers have nicknamed the Kraken. Since then, surprisingly, it seems that our galaxy has avoided any collisions with other large galaxies for nearly 10 billion years, a rare quiet period in galactic history. In contrast, our neighbouring Andromeda galaxy has had a much busier past, shaped by many more mergers with large galaxies. Today, both the Milky Way and Andromeda occupy a special place in what astronomers call the galaxy colour magnitude diagram. They're in the Green Valley, a region between the bright blue cloud of galaxies still forming stars and the red sequence of older galaxies, where star formation has nearly stopped. This means that the Milky Way's ability to make new stars is slowly fading as it runs low on the raw gas needed for star formation. Computer simulations show that within about 5 billion years, the Milky Way will probably stop forming stars entirely, though before that happens, its collision with the Andromeda galaxy may briefly trigger a burst of new star creation. Even now, the Milky Way is among the brightest and reddest of all spiral galaxies that still form stars. Yet compared to the oldest and reddest galaxies, it still shines with a faint hint of young blue light, a sign that life and motion still exist within its great spiral arms. To understand just how old the Milky Way really is, astronomers study its oldest surviving residents, globular clusters. These ancient star groups give us a lower limit on the galaxy's age. Scientists also measure the amount of long-lived radioactive elements like thorium-232 and uranium-238 in ancient stars. By comparing how much is left to how much there once was, they can estimate star ages using a method called nucleocosmochronology. This method shows that some stars, such as the star named CS 31082-001, are about 12.5 billion years old, while others, like BD plus 17 degrees 3248, may be as old as 13.8 billion years. White dwarfs, the small dim stars that have used up their fuel and are slowly cooling down, act like cosmic clocks, quietly keeping track of the ages of the universe. By measuring how cool the oldest of these stars have become, astronomers can estimate the age of star clusters. For example, the globular cluster known as M4 is thought to be about 12,700,000,000 years old. Some of the oldest clusters in our Milky Way galaxy are around 12.5 billion years old, with an extreme upper limit of perhaps 16 billion years. In November of the year 2018, astronomers made a stunning discovery. One of the oldest stars ever found in the entire universe. This tiny ancient star, officially named 2MASS J, 1808202-5104378b, is nearly 13,500,000,000 years old. Remarkably, it is composed almost entirely of primordial material from the Big Bang itself. Its presence within our Milky Way suggests that our galaxy may be at least 3 billion years older than scientists previously thought, stretching its history nearly back to the very dawn of time. Many individual stars discovered in the far outer regions of the Milky Way, in a vast halo surrounding the galaxy, are also incredibly old, approaching the estimated age of the universe, which is about 13,800,000,000 years. A famous example found in the year 2007 is a star called HE 1523-0901. Astronomers estimated its age at roughly 13,200,000,000 years, making it the oldest known object in our galaxy at that time. This ancient star helped researchers set a lower limit on the age of the Milky Way itself. To figure out these ages, astronomers use highly sensitive tools such as the UV Visual Echelle spectrograph on the Very Large Telescope in Chile. This instrument carefully analyzes the star's light and measures the faint spectral fingerprints of elements like thorium, created in massive nuclear reactions called the R process. By comparing the quantities of these elements and their isotopes, scientists can calculate how long ago they were formed. This technique, known as nucleocosmochronology, is like cosmic radioactive dating, revealing the timeline of the stars. Another fascinating star, HD 140283, has been studied many times. Its estimated age ranges between 12 billion and 13,700,000,000 years, depending on the method used. In the dense central bulge of the Milky Way, observations corrected for Earth's atmospheric distortions show stars that are about 12,800,000,000 years old. The stars in the Milky Way's thin disk, the flat, pancake-like region where most stars, gas and dust are concentrated, are generally much younger. Using the same cosmic dating methods, astronomers estimate that this disk began forming around 8,800,000,000 years ago, with a possible margin of error of 1 to 2 billion years. This suggests a long pause of nearly 5 billion years between the formation of the galaxy's halo and the creation of its disk. Further studies of the chemical makeup of thousands of stars indicate that star formation sharply declined between 10 billion and 8 billion years ago, likely because the gas between stars became too hot and chaotic to collapse into new stars as easily as before. Surrounding the Milky Way are many smaller companion galaxies, but they are not scattered randomly. Instead, they appear to form a huge ring-like structure about 500,000 light-years across and 50,000 light-years thick. Astronomers think this pattern may have formed long ago when a larger system broke apart. Close encounters between galaxies, such as the future collision expected about 4 billion years from now between the Milky Way and the Andromeda Galaxy, can strip away enormous streams of gas. Over time, these streams can condense into new dwarf galaxies that orbit in rings at different angles around the main galaxy. The Milky Way and Andromeda together form a kind of cosmic pair, two giant spiral galaxies bound in a loose binary system. They are part of a cluster of about 50 galaxies called the local group. Surrounding the local group is a vast empty space called the local void, and this lies within an even larger structure known as the local sheet, which itself is part of the massive Virgo supercluster. Around this supercluster lie immense cosmic voids, the Microscopium void to the north, the Sculptor void to the left, the Bodes void to the right, and the Cain's major void to the south. These voids are not fixed. They slowly move and shift over time, forming long, web-like structures of galaxies called filaments. The Virgo supercluster is being pulled toward an even larger gravitational area known as the Great Attractor, which is part of the colossal cosmic structure called Laniakea, the grand home of our galaxy in the universe. Among the Milky Way's companions, the largest are the Large and Small Magellanic Clouds, two irregular dwarf galaxies. The Large Magellanic Cloud is about 32,200 light-years across and orbits near its smaller companion. Stretching from these galaxies is the Magellanic Stream, a long ribbon of neutral hydrogen gas that extends across 100 degrees of the night sky. This stream was likely pulled from the two galaxies by the Milky Way's gravity during their past encounters. Many smaller dwarf galaxies also circle our Milky Way. These include the closest, the Canis Major Dwarf, along with the Sagittarius Dwarf elliptical galaxy, the Ursa Minor Dwarf, the Sculptor Dwarf, the Sextans Dwarf, the Fornax Dwarf, and the Leo 1 Dwarf. The tiniest of these, such as the Carina Dwarf, Draco Dwarf, and Leo 2 Dwarf, are only about 500 light-years wide, a mere speck compared to our galaxy. Astronomers continue to discover new faint companions. In the year 2015, 9 previously unknown satellite galaxies were found in just a small part of the sky. Some of these dwarf galaxies have already been absorbed into the Milky Way, including the ancient progenitor of the enormous globular cluster called Omega Centauri. In the year 2005, and confirmed once again in 2012, scientists announced a truly astonishing discovery about our home galaxy. They found that most of the Milky Way's smaller companion galaxies, called satellite galaxies, are not scattered randomly as previously thought, but instead line up in a single, enormous flat disk, all moving in roughly the same direction. This was completely unexpected because the standard ideas about how galaxies form suggest that these smaller galaxies should be spread out in all directions, each orbiting in its own way within invisible halos of dark matter. Why these galaxies are so neatly arranged remains one of the most puzzling mysteries of the cosmos. Only a year later, in January of 2006, researchers solved another long-standing enigma: the strange warp of the Milky Way's own disk. By making extremely detailed maps of the galaxy, they discovered that the bend is not permanent but a kind of ripple, a vibration caused by the gravitational pull of the Large and Small Magellanic Clouds as they orbit around the Milky Way. Though these two neighbouring galaxies contain only about 2% of the Milky Way's total mass, computer simulations reveal that their motion through the outer reaches of our galaxy stirs up the dark matter, creating a wake that magnifies their effect. The result is a wobble in the galactic disk, much like the ripples spreading across a pond after tossing in a stone. Turning our gaze outward, we know that the Andromeda Galaxy, our nearest large galactic neighbour, is hurtling toward the Milky Way at a speed of roughly 100 to 140 kilometers per second, which is about 220,000 to 310,000 miles per hour. At this rate, in approximately 4 billion and 300 million years, the two galaxies are expected to collide. But despite this dramatic rendezvous, the chance of two individual stars actually crashing into each other is astronomically small because the stars are separated by such vast distances. Instead, the gravitational pull between the galaxies will gradually merge them into a single enormous galaxy, likely an elliptical or a massive disk-shaped galaxy, over the next 6 billion years, forever reshaping the night sky as we know it. Einstein's theory of special relativity tells us that there is no single, absolute viewpoint in space from which we can measure motion. However, astronomers can describe the Milky Way's motion in relation to larger cosmic structures. One such point of reference is called the Hubble flow, which is the apparent movement of galaxies caused by the expansion of the universe itself. Every galaxy, including our Milky Way, has its own unique speed and direction known as peculiar velocity, which is slightly different from the smooth outward stretch of space. To compare the Milky Way's motion to this overall cosmic expansion, astronomers must look at a huge region of the universe, large enough that the general expansion outweighs the smaller, random motions of individual galaxies. When averaged over such vast distances, the motion of all galaxies aligns with the Hubble flow. Careful measurements show that the Milky Way is moving at roughly 630 kilometers per second, which is about 1,400,000 miles per hour relative to this large-scale cosmic frame. This incredible speed is directed generally toward a mysterious gravitational anomaly called the Great Attractor, which pulls many nearby galaxies, as well as toward the even larger Shapley supercluster beyond it. Our galaxy, together with the Andromeda Galaxy and dozens of smaller companions, forms a gravitationally bound collection called the Local Group. This group is part of an even larger structure called the Local Supercluster, centered near the Virgo cluster. Though the Local Group and the Virgo cluster are moving apart at about 967 kilometers per second, or roughly 2,160,000 miles per hour, this separation is still slower than what would be expected if they were moving solely due to the expansion of the universe at their enormous distance of about 16.8 million parsecs. Scientists believe this slower movement is caused by the strong gravitational pull between these colossal cosmic structures. Another way astronomers measure the Milky Way's motion is by observing the cosmic microwave background, the faint glow left over from the universe's birth. In this frame of reference, scientists look for the direction where this afterglow is most uniform, showing no distortion caused by motion. Using this method, they found that the Milky Way is moving at approximately 552 kilometers per second, plus or minus 6 kilometers per second, which is about 1,235,000 miles per hour, toward a spot in the sky near the constellation Hydra, at roughly 10.5 hours of right ascension and 24 degrees south declination. This extraordinary motion has been directly observed by satellites such as the Cosmic Background Explorer, known as COBE, and the Wilkinson Microwave Anisotropy Probe, or WMAP. These spacecraft detect a subtle pattern in the cosmic microwave background called the dipole anisotropy, a tiny difference in temperature caused by the Milky Way's motion. In the direction the galaxy is travelling, the light from the CMB appears slightly blue-shifted, meaning its waves are compressed and therefore hotter. In the opposite direction, the light is red-shifted, with stretched waves that appear cooler. The Cigar Galaxy is one of the most amazing and active galaxies near us. It is about 12 million light-years away from Earth in the northern constellation of Ursa Major, the Great Bear. Within its local group of galaxies, called the M81 group, it is the second largest member. Across its visible span, measured as a D25 isophotral diameter, it stretches about 12.52 kiloparsecs, or roughly 40,800 light-years. This galaxy shines with incredible brightness. It is nearly 5 times brighter than our Milky Way, and its central area alone glows about 100 times more. The reason for this strong light is the galaxy's amazing starburst activity, a cosmic fireworks show where new stars are forming very quickly. Astronomers think this burst of star-making was caused by the pull and interaction with its nearby galaxy, M81. Because it is close to Earth and has such extreme star-forming activity, M82 is often seen as the perfect example, or model, of a starburst galaxy. In the year 2014, astronomers saw a dramatic event in M82. A bright type Ia supernova, called SN2014J, exploded on the 21st of January. That same year, researchers also found an extraordinary pulsar, an extremely dense, fast-spinning remnant of a massive star called 82X2. It turned out to be the brightest pulsar ever found, a record-breaking cosmic lighthouse shining across space. Almost 10 years later, in November of 2023, another amazing event happened. Astronomers detected a strong gamma-ray burst coming from M82. Careful observation showed that the explosion came from a magneta, a type of neutron star with an extremely strong magnetic field. This was the first time such an event had been seen outside our Milky Way galaxy, and only the fourth time ever recorded anywhere in the universe. The story of M82 goes back much further. It was first seen in the year 1774 by the German astronomer Johann Elert Bode, who described it as a faint hazy patch of light lying about 3/4 of a degree away from another similar object, M81. Just a few years later, in 1779, the French astronomer Pierre Méchain found both galaxies again and reported them to Charles Messier, who soon added them to his famous catalogue of space objects. For a long time, M82 was thought to be an irregular galaxy, meaning it had no clear shape or spiral structure. But in the year 2005, new observations using near-infrared light showed something surprising. Two smooth spiral arms hidden within the galaxy's bright disk. These arms had not been seen before because the galaxy is seen almost edge-on from Earth, tilted at about 80 degrees, and its central regions are covered in thick, dusty filaments that block visible light. When astronomers carefully removed the background glow from their infrared images, the spiral arms became visible. They appeared bluer than the disk, showing they were full of young, hot stars. The arms seemed to curve outward from the ends of a central bar of stars, stretching across about 3 times the width of the disk. That same year, the Hubble Space Telescope revealed an incredible sight in M82's core. 197 massive clusters of newly formed stars. Each cluster had on average about 200,000 times the mass of our Sun, making the galaxy's centre extremely active and crowded. New stars there are being born about 10 times faster than in the entire Milky Way galaxy. At the very centre of M82 is a strong starburst area about 500 parsecs across. Inside this small space, astronomers found 4 very bright zones, called A, C, D, and E. These clumps shine strongly in visible light and also match known sources of X-rays, infrared light and radio waves. The galaxy's famous superwind, a huge outflow of gas and dust powered by exploding stars, seems to come mostly from clumps A and C. Supernovae happen there about once every 10 years, sending enough energy to push material out of the galaxy's centre and into space like smoke from a cosmic chimney. The Chandra X-ray Observatory later found strange flickering X-rays about 600 light-years from the galaxy's centre. Astronomers think they may come from a rare type of black hole, one that is medium-sized, with a mass about 205,000 times that of the Sun. Like most large galaxies, M82 also has a supermassive black hole at its centre, weighing about 30 million times the mass of the Sun, as measured by the motion of nearby stars. In April of 2010, radio astronomers at the Jodrell Bank Observatory in the United Kingdom found something unexpected in M82. They detected a new radio source that began sending out unusual signals unlike anything seen before. The object's strange behaviour was hard to explain. Some scientists suggested it might be a rare type of microquasar, a small but powerful object that shoots out jets of material nearly at the speed of light. However, unlike known microquasars, this one gave off very little X-ray radiation, so little that it could not be measured. The mysterious object is several arc seconds away from the galaxy's centre, making it unlikely to be connected directly to its supermassive black hole. Even more puzzling, it seems to move at an apparent speed 4 times faster than light. This illusion of faster-than-light motion happens when strong jets of material move almost directly toward us at nearly the speed of light, making them appear faster than light. Messier 82, also called the Cigar Galaxy, lives under the strong influence of its larger neighbour, the big spiral galaxy Messier 81. The two galaxies are locked in a cosmic dance, and the strong pull of Messier 81's gravity has been slowly stretching and reshaping Messier 82 for about 100 million years. This gravitational tug-of-war has stirred up the gas and dust inside Messier 82, causing a big increase in star formation, about 10 times more than in normal galaxies. Over the past 200 million years, Messier 82 has had at least one major close encounter with Messier 81. During this time, huge streams of gas were pulled toward the galaxy's centre. The strongest of these encounters probably happened between 200 million and 500 million years ago, and it caused a huge burst of star creation in the galaxy's heart. This starburst phase lasted for up to 50 million years, with new stars being born at a rate of about 10 times the mass of our Sun every year. After that, 2 more smaller starbursts happened, with the most recent one about 4 to 6 million years ago. This event created the galaxy's bright central clusters, a mix of huge superstar clusters and smaller companions. Farther out in the disk of Messier 82, most stars were made during a great wave of star formation about 500 million years ago. This left the galaxy's disk filled with hundreds of young clusters that look like the old globular clusters in our Milky Way, though much younger. Around 100 million years ago, this outer star formation stopped completely. Since then, almost all star-making in Messier 82 has been in its bright active centre, with only weak activity continuing in the outer halo over the past 1 billion years. Scientists think that long ago, Messier 82 may have been a faint, quiet galaxy. Its violent change likely started when it came under the gravity of the massive Messier 81, which awakened the galaxy's hidden energy and triggered its amazing bursts of star formation. From Earth, the centres of Messier 81 and Messier 82 seem to be about 130,000 light-years apart. Their actual distance is estimated to be around 300,000 light-years, give or take a few 100,000. Because it is a starburst galaxy, Messier 82 often produces supernovae, huge explosions marking the death of massive young stars. The first candidate for a supernova in this galaxy, called SN 1986d, was later found not to be a real supernova but a variable infrared source instead. The first confirmed supernova in Messier 82 was found in March of 2004. Called SN 2004 AM, it was seen in images taken a few months earlier, in November of 2003 by the Lick Observatory Supernova Search. Scientists later identified it as a Type II supernova, the explosive collapse of a massive star. In the year 2008, astronomers noticed a strange burst of radio waves coming from a galaxy known as Messier 82. This mysterious signal, called SN 2008IZ, was likely caused by a supernova, a powerful star explosion, but it was hidden behind thick clouds of gas and dust, making it invisible to ordinary telescopes that rely on normal light. Interestingly, a similar radio-only signal appeared the following year, in 2009, though this second event was never officially confirmed or given a formal name. Before detailed modern surveys were conducted, scientists believe that Messier 82 probably experienced many other supernova explosions during earlier decades. In the 1980s and 1990s, astronomers using the European Very Long Baseline Interferometry Network carefully studied several possible remnants of old supernovae within the galaxy. One of these remnants was seen expanding noticeably between the years 1986 and 1997, suggesting that the original star explosion had occurred sometime in the early 1960s. 2 other remnants showed hints of possible expansion as well, though their exact ages could not be confirmed with certainty. Then, on the 21st of January in the year 2014, at 19 hours and 20 minutes Universal Time, a new bright point of light suddenly appeared in Messier 82. This discovery was made by Steve Fossey, a lecturer in astrophysics, along with 4 of his students at the University of London Observatory. Initially, the object appeared at a brightness called magnitude plus 11.7. Within just 2 days, it had brightened to magnitude plus 10.9. Examination of earlier photographs showed that it had begun brightening sometime between the 14th and the 20th of January, rising from magnitude plus 14.4 to plus 11.3. At first, astronomers hoped it might reach magnitude plus 8.5, which would have made it easily visible even with small telescopes or large binoculars. However, by the end of January, the supernova reached a slightly dimmer peak of magnitude plus 10.5. Later studies revealed that this was a young reddened Type 1a supernova, the dramatic explosion of a white dwarf star in a binary star system. The International Astronomical Union officially named it SN 2014J. Interestingly, Messier 82's larger neighbouring galaxy, Messier 81, had previously hosted another famous supernova, SN 1993J, and although SN 1987A in the Large Magellanic Cloud occurred much closer to Earth, SN 2014, J still represents the closest Type 1a supernova observed since SN in 1972E. Such events are extremely rare, making SN 2014J a truly remarkable and memorable milestone in modern astronomy and the study of galaxies. The Andromeda Galaxy is what astronomers call a barred spiral galaxy. This means that its spiral arms stretch outward elegantly from a bright, bar-shaped core, creating a graceful cosmic whirl. Andromeda is also the closest large galaxy to our own Milky Way. Long before astronomers fully understood what galaxies were, people called it the Andromeda Nebula. This enormous galaxy spans an incredible width of about 152,000 light-years, making it almost twice as wide as the Milky Way. This vast size makes Andromeda the largest member of our local cosmic neighbourhood, known as the Local Group of Galaxies. It sits at a tremendous distance of roughly 2.5 million light-years from Earth, or about 765,000 parsecs in space speak. To put that into perspective, the light you are seeing from Andromeda tonight began its journey toward us roughly 2.5 million years ago, a time when early humans on Earth were just beginning to shape simple stone tools. The name Andromeda comes from the constellation where it appears in the sky. This constellation is named after a princess from ancient Greek mythology who was rescued by the hero Perseus, giving the galaxy a link not only to science, but also to some of the oldest stories ever told by humans. In terms of its total mass, Andromeda weighs about the same as the Milky Way. Both galaxies are estimated to have a mass roughly equivalent to 1 trillion times that of our Sun, an almost unimaginable number, about 2 times 10 to the power of 42 kilograms. For a long time, scientists thought Andromeda was significantly heavier than the Milky Way, perhaps by 25 to 50%. However, more precise studies in the early 21st century revealed that the two galaxies are actually much closer in weight than previously thought, and some research even suggests that the Milky Way might be slightly heavier. These two massive galaxies are not stationary. They are slowly moving toward each other under the force of gravity. In about 10 billion years, they are expected to collide and merge into a single colossal galaxy. This new galaxy might take the shape of a bright round elliptical galaxy or a smooth lens-like galaxy. This future cosmic encounter will dramatically change the night sky, though by that time, the Sun will likely have transformed into a red giant, and Earth as we know it may no longer exist. Even today, Andromeda is one of the brightest objects in the deep sky visible from Earth. With an apparent brightness of around 3.5, it can be seen without a telescope on a clear, dark night, even in areas with some light pollution. To the naked eye, it appears as a soft, misty patch of light, a faint ghostly glow stretching across the darkness. Ancient peoples may have noticed it long before telescopes existed. Some historians believe the ancient Babylonians even recorded Andromeda as part of a constellation they called the Rainbow of the Sky. The first clear written description of Andromeda comes from the Persian astronomer Abd al-Rahman al-Sufi, who, around the year 964, described it in his Book of Fixed Stars as a small cloud or faint smear. This account, written more than 1,000 years ago, is the oldest known record of a galaxy other than the Milky Way. For centuries afterward, astronomers referred to it simply as the Little Cloud. In the early 17th century, in the year 1612, the German astronomer Simon Marius was one of the first to observe Andromeda through a telescope. Later, the British astronomer John Flamsteed recorded it as 33 Andromeda. In 1745, the French scientist Pierre-Louis Maupertuis proposed a bold idea, that this fuzzy patch of light might actually be an island universe, a distant system of stars separate from our own. Then, in 1764, the famous French astronomer Charles Messier added it to his catalogue of celestial objects as M31. Messier incorrectly credited Marius as its discoverer, even though Andromeda had been visible to the naked eye since ancient times. By 1785, the renowned astronomer William Herschel noticed that Andromeda's centre had a faint reddish tint. He believed it was the closest of all the great nebulae and, based on its brightness, estimated it to be about 18,000 light-years away, an error by modern standards, but an impressive attempt given the knowledge and tools of his time. In the middle of the 19th century, in the year 1850, a brilliant astronomer named William Parsons, who was also called the third Earl of Rosse, created one of the first drawings that clearly showed the spiral shape of the Andromeda galaxy. This was a huge step forward for science, because at the time most people thought that faint nebulae were just clouds of gas floating in space. Parsons' work hinted at something far greater. These nebulae could actually be enormous systems made of countless stars, each with its own structure and shape. A little later, in the year 1864, another astronomer named William Huggins studied the light coming from Andromeda through a device called a spectroscope. What he found astonished him. The pattern of the light did not look like it came from a simple gas cloud. Instead, it resembled the mixed light of many stars shining together. This discovery proved that Andromeda was made of stars, a galaxy in its own right, and not merely a diffuse nebula. Then, in the year 1885, something extraordinary happened. A bright new point of light appeared in Andromeda. Today, we know it was a supernova, an exploding star, but at the time, astronomers called it Nova 1885 because they did not yet understand the difference between ordinary novae and supernovae. Remarkably, this is the only supernova ever observed in Andromeda. Just a few years later, in 1888, the astronomer Isaac Roberts took one of the very first long-exposure photographs of the galaxy. His picture revealed Andromeda's spiral arms in stunning detail, though he still mistakenly believed it was part of the Milky Way, a misunderstanding common at the time. By the early years of the 20th century, more clues began to emerge that would change everything we thought about the universe. In the year 1912, the astronomer Vesto Slipher used spectroscopy to measure how Andromeda was moving. To everyone's surprise, he discovered it was rushing toward us at an incredible speed of roughly 300 kilometers per second, faster than any other known object of the time. This finding began to reveal a completely new vision of the universe, showing that galaxies were massive, separate systems scattered across the vast cosmos. Interestingly, the philosopher Immanuel Kant had already imagined something like this as far back as the year 1755. In his book, Universal Natural History and Theory of the Heavens, he suggested that the Milky Way was just one of countless island universes, what we now call galaxies, floating through the immense expanse of space. Kant's visionary ideas anticipated discoveries that would take more than a century and a half to confirm. In the year 1917, another important discovery occurred when the American astronomer Heber Curtis studied a nova in Andromeda and found 11 more in older photographs. He noticed that these novae were about 10 times fainter than similar events seen elsewhere in the sky. From this, he calculated that Andromeda must be around 500,000 light-years away, far beyond the edge of the Milky Way. While this was still smaller than the actual distance, it was enough to prove that Andromeda was not a nearby nebula, but a galaxy in its own right. This supported the bold island universe idea, that the universe is filled with countless galaxies, each containing billions of stars. Andromeda, once thought to be a simple cloud floating near us, was revealed to be a majestic spiral galaxy, similar in size and structure to our own Milky Way, drifting through the endless darkness of space alongside us. In the early decades of the 20th century, astronomers were still unraveling the universe's deepest secrets. One of the most famous debates in scientific history took place in the year 1920, when two astronomers, Harlow Shapley and Heber Curtis, engaged in a heated argument known as the Great Debate. They discussed the true nature of the Milky Way, the mysterious spiral nebulae seen in telescopes, and the real size of the universe. Curtis argued passionately that the Great Andromeda Nebula was not part of our galaxy, but a completely separate island universe, a galaxy far beyond the Milky Way. He pointed to the dark lanes in Andromeda that resembled the dust clouds in our own galaxy, and referenced earlier measurements showing that it was moving as a distinct distant system, rather than a nearby cloud of gas. Just 2 years later, in the year 1922, the Estonian astronomer Ernst Öpik devised a clever method to calculate Andromeda's distance. By studying the movement of its stars, he estimated that it lay roughly 450 kiloparsecs away, about 1.5 million light-years, placing it far beyond the Milky Way. This was a revolutionary idea at the time, revealing that our galaxy was just one of many in a universe full of galaxies. The next major breakthrough came with Edwin Hubble, who forever changed humanity's understanding of the cosmos. In the year 1925, using the massive 100-inch Hooker telescope at Mount Wilson Observatory, he discovered a special type of star in Andromeda called Cepheid variables. These stars brighten and dim in a regular pattern, which allows astronomers to measure their true distances. Hubble's careful observations and photographs finally proved beyond any doubt that the Great Andromeda Nebula was not part of our Milky Way. It was a separate galaxy, millions of light-years away. Hubble's work ended the Great Debate and expanded our view of the universe on an unimaginable scale. 2 decades later, in the year 1943, Walter Baade became the first astronomer to clearly see individual stars in the centre of Andromeda. By studying them, he discovered that these stars belonged to 2 distinct groups. The younger, hotter, faster stars in the galaxy's disk he called Type 1, while the older, cooler, redder stars in the central bulge he called Type 2. This classification, later used for stars in other galaxies, helped scientists understand that galaxies, like stars, evolve and age over time. They had also discovered 2 different kinds of Cepheid variables, which meant earlier distance measurements, including those for Andromeda, had been too small. Once corrected, the new calculations nearly double the estimated distance to Andromeda, and, by extension, the known size of the universe itself, a revelation that reshaped astronomy overnight. By the middle of the 20th century, advances in technology were opening an entirely new way of exploring the universe. Astronomers were no longer limited to the light we can see with our eyes. They could now detect radio waves, X-rays, and other forms of invisible light, revealing secrets of galaxies that had remained hidden for millennia. In the year 1950, at Jodrell Bank Observatory, 2 pioneering scientists, Robert Hanbury Brown and Cyril Hazard, detected radio waves coming from the Andromeda galaxy for the very first time. This breakthrough showed that Andromeda was more than just a distant smudge of light. It was a dynamic, active galaxy. Only a few years later, still in the 1950s, John Baldwin and his team at the Cambridge Radio Astronomy Group created the first radio maps of Andromeda. These maps revealed powerful energetic activity at its core, activity that ordinary telescopes could never see. In recognition of its brilliance in radio waves, Andromeda's glowing centre was catalogued in the second Cambridge Radio Catalogue as 2C56. Then, in the year 1959, a trio of astronomers, André Lallemand, Monsieur Duchenne, and Merle Walker, made a shocking discovery. The very heart of Andromeda was spinning at incredible speed. Using the 120-inch telescope at Lick Observatory, along with Lallemand's groundbreaking electron camera, they calculated that the galaxy's core had a mass roughly 13 million times that of our Sun. Just 2 years later, in 1961, Merle Walker found something similar in a neighbouring small galaxy, Messier 32, where the central mass was close to 10 million suns. These early discoveries hinted at an astonishing secret hiding at the centres of galaxies, a secret we now know as supermassive black holes, the colossal engines that power the hearts of galaxies. As decades passed, Andromeda continued to reveal its mysteries. In the year 2009, astronomers observed a rare cosmic event known as microlensing. This occurs when the light from a distant object bends because a heavy body passes in front of it, acting like a natural magnifying glass. This unusual phenomenon might have been the very first glimpse of a planet inside the Andromeda galaxy, a thrilling hint that distant worlds could exist far beyond our own Milky Way. More astonishing revelations followed. In the year 2020, astronomers using a combination of powerful radio telescopes, the Westerbork Synthesis Radio Telescope, the Effelsberg 100-meter radio telescope, and the Very Large Array, discovered that Andromeda's magnetic fields were perfectly aligned along a vast ring of gas and star formation, stretching 10 kiloparsecs across. This finding showed that magnetic forces play a major role in shaping the galaxy's elegant spiral arms, adding yet another layer to its intricate beauty. Then, in the year 2023, a remarkable discovery came not from professional observatories, but from a group of dedicated amateur astronomers, Marcel Drexler, Xavier Strotner, and Jan Sainty. They detected a massive faint cloud rich in oxygen, lying just south of Andromeda near a bright star called 35 Andromeda. Named SDSO1, this ghostly cloud was so dim that it required many hours of careful observation to capture its ethereal glow, visible only in the light of doubly ionized oxygen. Initially, scientists thought SDSO1 might be an object outside our Milky Way, perhaps formed where the halos of Andromeda and the Milky Way overlapped. Later studies, however, using spectroscopy, revealed that the cloud is actually part of our own galaxy. Current theories suggest it may be a bow shock, a glowing arc of gas formed as a dying double-star system, e.g. Andromeda, moves through surrounding interstellar material. In the year 2025, the National Aeronautics and Space Administration shared one of the most detailed images of Andromeda ever created. By combining over 600 separate photographs taken by the Hubble Space Telescope over 10 years, astronomers assembled a massive mosaic showing hundreds of millions of individual stars. Among these, about 200 million shone brighter and hotter than our Sun, though this is only a fraction of Andromeda's total stellar population. Earlier in the 20th century, in 1953, astronomers made another key discovery: a second, dimmer type of Cepheid variable star. This finding dramatically doubled the estimated distance between the Milky Way and Andromeda. In the final decade of the 20th century, scientists refined these distance measurements further, using data from the European Space Agency's Hipparcos satellite. By carefully studying both red giant stars and red clump stars, astronomers improved the Cepheid distance scale, bringing ever more precision to our understanding of how far Andromeda really is from us. Andromeda's story stretches far beyond human observation, deep into the galaxy's ancient past. Between 2 and 3 billion years ago, a titanic collision occurred. Two large galaxies smashed together in a cosmic merger near where Andromeda now sits. The larger galaxy was roughly 4 times the mass of its smaller partner, and their violent encounter left permanent marks on Andromeda's structure. Astronomers discovered this ancient collision by studying the ages and motions of Andromeda's stars, which did not match what would be expected in a calm, orderly galaxy. Around 2 billion years ago, star formation across Andromeda's broad disk surged dramatically, clear evidence of this cosmic upheaval. Using sophisticated computer simulations, scientists recreated this ancient galactic crash and discovered that it likely formed many of the galaxy's current features. The merger may have created Andromeda's metal-rich halo, the giant stellar stream, and both its thick and thin disks. It might even have formed a massive circular ring about 10,000 parsecs from the centre. During this turbulent time, Andromeda's star formation rate was so intense that the galaxy briefly shone as a luminous infrared galaxy, radiating brightly in infrared light for nearly 100 million years. These same models also recreated the central bulge, the large bar-shaped structure, and the thickness of the outer halo, showing how one ancient violent collision shaped much of the galaxy we marvel at today. For a long time, astronomers wondered whether the massive Andromeda galaxy and its smaller neighbour, the Triangulum galaxy, also known as Messier 33, might have come very close to each other somewhere between 2 and 4 billion years ago. It was a tempting idea because such a close encounter could have affected the structure and motion of both galaxies. However, later, far more precise measurements taken by the Hubble Space Telescope revealed that this near collision was highly unlikely, putting that theory to rest. Determining the exact distance from Earth to Andromeda has always been a tricky challenge. Over the years, astronomers have tried at least 4 different methods, each bringing them closer to the truth. In the early years of the 21st century, entirely new techniques allowed for even greater accuracy. In the year 2003, scientists used a method called infrared surface brightness fluctuations and corrected for the effects of metallicity, essentially the amount of heavy elements in stars, to estimate that Andromeda lies about 2,570,000 light-years away. The following year, using the more traditional approach with Cepheid variable stars, they found a slightly smaller distance of roughly 2,510,000 light-years. Then, in the year 2005, astronomers made a remarkable discovery: a pair of hot blue stars in Andromeda forming an eclipsing binary system. By carefully observing how the brightness of these stars dipped as they passed in front of one another, scientists could calculate their exact sizes and luminosities. From this, they determined that the binary system was about 2,520,000 light-years from Earth, implying that the rest of Andromeda was almost at the same distance. Another method, known as the tip of the red giant branch technique, gave a similar figure of about 2,560,000 light-years. When all these measurements were combined, the average distance to Andromeda was calculated to be roughly 2,540,000 light-years, a number modern astronomers still rely on with great confidence. For many decades, the total mass of the Andromeda galaxy was also a subject of debate. Until the year 2018, most estimates suggested that Andromeda's halo, including its enormous amount of dark matter, had a mass of about 1.5 trillion times the mass of our Sun, slightly larger than the Milky Way's estimated 800 billion solar masses. Some earlier studies, however, hinted that both galaxies might actually have very similar masses. Then, in 2018, new observations using radio telescopes supported this idea, indicating that the Milky Way and Andromeda are likely almost equal in total mass, each holding around 800 billion solar masses. Further studies in the early 21st century revealed more about Andromeda's structure. Its rounded central region is much denser with stars than the Milky Way's core, and its sprawling disk stretches nearly twice as wide as our own galaxy's disk. Depending on the method used, Andromeda's total mass is thought to range between 800 billion and just over 1 trillion solar masses. Of this, approximately 100 to 150 billion solar masses are made of stars. Nearly 1/3 of these stars are concentrated in the central bulge, a little over half are spread across the galactic disk, and the rest are scattered throughout the halo. By the year 2019, newer studies based on measurements of stellar escape speeds and motions suggested that Andromeda's total mass might be closer to 800 billion solar masses, roughly half the Milky Way's, which by that time was thought to contain about 1.5 trillion solar masses. But stars are only part of Andromeda's story. The galaxy also contains enormous amounts of gas and dust. Its interstellar material includes at least 7 billion solar masses of neutral hydrogen, more than 300 million solar masses of molecular hydrogen within its inner 10,000 parsecs, and around 50 million solar masses of cosmic dust. Surrounding the galaxy is an enormous, almost invisible halo of hot gas, stretching nearly 1 million light-years into space, almost halfway to the Milky Way. This halo could contain roughly half as much mass as all the stars in Andromeda itself. Astronomers believe this vast halo formed alongside the galaxy billions of years ago, enriched with heavy elements created by countless supernova explosions. Every time a massive star in Andromeda's disk ended its life in a spectacular supernova, it hurled elements like carbon, oxygen, and iron far into space, gradually filling the halo with this cosmic material. Over the course of billions of years, nearly half of all the heavy elements ever produced by Andromeda's stars have been blown well beyond its visible disk, which itself stretches about 200,000 light-years across. Andromeda shines brilliantly, with a total luminosity of about 26 billion times that of the Sun, roughly 25% brighter than our Milky Way. However, because we see it at a steep angle from Earth, much of its light is blocked by interstellar dust drifting through its broad spiral arms, making its true brightness difficult to measure. Some astronomers even believe Andromeda may be the second brightest galaxy within a radius of 10 megaparsecs around the Milky Way, outshone only by the elegant Sombrero galaxy. Its absolute magnitude is estimated at around -22.21, though slight variations appear in different studies. In the year 2010, astronomers using the powerful Spitzer Space Telescope made fascinating measurements of the Andromeda Galaxy. They found that its true brightness in the blue portion of visible light is approximately minus 20.89. When factoring in its colour index of plus 0.63, this translates to a visual brightness of around minus 21.52. By comparison, our own Milky Way galaxy shines at roughly minus 20.9 in the same measure. At this wavelength, the total light emitted by Andromeda was estimated to be about 3.64 times 10 to the power of 10 times the brightness of our Sun, making it one of the most luminous galaxies in our local cosmic neighbourhood. Despite this impressive radiance, Andromeda's current rate of star formation is surprisingly modest. Each year, it produces roughly the equivalent of one Sun's mass in new stars, while the Milky Way creates about 3 to 5 times that amount annually. Even the frequency of novae, those dramatic star explosions that briefly make a galaxy glow, is nearly twice as high in our Milky Way as in Andromeda. This contrast suggests that Andromeda likely experienced a spectacular period of intense starbirth long ago, but today it rests in a quieter, more settled phase of its life. Meanwhile, our Milky Way continues to flourish with youthful energy, filling its spiral arms with new stars. If this pattern continues, our galaxy's total brightness could one day surpass that of Andromeda. Modern studies place Andromeda in what astronomers call the Green Valley on the galaxy colour brightness chart. This is a transitional zone between the blue cloud, where galaxies are still actively forming stars, and the red sequence, which is populated by older galaxies that have mostly stopped creating new stars. Galaxies in the Green Valley, like Andromeda and the Milky Way, are gradually running out of the gas and dust needed to make new stars. According to computer models, Andromeda is expected to cease star formation entirely within roughly 5 billion years, even after a temporary surge of new stars that could occur when Andromeda and the Milky Way eventually collide and merge. In visible light, Andromeda is classified as an SASB galaxy under the Dwarf sondage system, a method astronomers use to categorize spiral galaxies by shape and structure. However, infrared observations from the 2-micron all-sky survey and the Spitzer Space Telescope revealed a hidden detail. Andromeda, like the Milky Way, has a central bar-shaped structure. This elongated bar is tilted about 55 degrees counterclockwise relative to the main disk, giving its spiral arms a graceful and distinctive curve. Measuring the exact size of a galaxy has always been a topic of debate among astronomers, since different methods often produce different results. A common standard is called the D25 isophote, which defines the region where a galaxy's blue light drops to 25 magnitudes per square arc second. According to the third reference catalogue of bright galaxies, published in 1991, Andromeda's D25 diameter is approximately 46.56 kiloparsecs, which equals roughly 152,000 light-years at a distance of about 2.5 million light-years from Earth. An earlier estimate from 1980 gave a slightly larger diameter of 54 kiloparsecs, or about 176,000 light-years. In 2005, observations using the Keck telescopes uncovered a faint, ghostly halo of stars extending far beyond Andromeda's bright spiral arms. These outer halo stars move in a more chaotic manner compared with the orderly rotation of stars in the galaxy's main disk, which orbit at about 200 kilometers per second. This diffuse halo stretches to roughly 67.45 kiloparsecs, or about 220,000 light-years, forming an enormous sphere of dim starlight around the galaxy. From our vantage point on Earth, Andromeda appears tilted at an angle of about 77 degrees. Were it tilted to 90 degrees, we would see it perfectly edge-on. Detailed studies reveal that Andromeda's disk is not completely flat, but instead has a gentle S-shaped bend. Astronomers believe this warp may be caused by the gravitational pull of nearby smaller galaxies, possibly including Messier 33, whose gravity might subtly twist Andromeda's majestic spiral arms. Careful measurements of Andromeda's rotation at different distances from its bright centre have revealed intriguing patterns. Near the core, approximately 1,300 light-years from the centre, stars move at roughly 225 kilometers per second. Farther out, at around 7,000 light-years, the speed drops to about 50 kilometers per second, then rises again to reach 250 kilometers per second at roughly 33,000 light-years. Beyond this, the rotation gradually slows, falling to around 200 kilometers per second at a distance of 80,000 light-years. These velocity patterns indicate that Andromeda's central region contains a highly concentrated mass of about 6 times 10 to the power of 9 solar masses, with the total mass continuing to increase steadily out to roughly 45,000 light-years before tapering off more gradually. The spiral arms of the Andromeda Galaxy sparkle with the light of countless H2 regions, immense clouds of hydrogen gas that glow because of newly formed stars within them. These luminous patches were studied in detail by the German-American astronomer Walter Baade, who famously described them as looking like beads on a string. Through his careful observations, Baade revealed 2 magnificent spiral arms that, while wound tightly, are spaced farther apart than the arms of our own Milky Way. This wider spacing gives Andromeda its uniquely elegant shape, as it drifts silently across the dark ocean of space. From Earth, we see Andromeda at a sharp angle, nearly edge-on, which hides much of its graceful spiral beauty. This tilt has made it quite tricky for astronomers to determine the exact layout of its arms. But when scientists use special techniques to digitally straighten out the galaxy, Andromeda revealed a spiral form that seems fairly typical. 2 large arms sweep outward from the galaxy's bright core, each separated by at least 13,000 light-years, an astonishing distance equivalent to roughly 820 million astronomical units. These arms begin their journey about 1,600 light-years, or 100 million astronomical units, from the glowing centre, reaching outward in a grand cosmic dance. However, not all astronomers agree on this picture. Some argue that Andromeda might have only a single arm, while others believe its arms form a softer, more irregular pattern, like a delicate web of long, thick strands rather than smooth, neat curves. Much of the bending and twisting of Andromeda's spiral arms is thought to be caused by the gravitational pull of its smaller neighbouring galaxies, Messier 32 and Messier 110. Evidence of this influence can be seen in the strange motions of neutral hydrogen clouds, which appear to drift away from the paths of the galaxy's stars, as if invisible cosmic hands were tugging at them. In the year 1998, the European Space Agency's Infrared Space Observatory revealed a surprising new perspective of Andromeda. The galaxy's shape appeared to be slowly transforming into what astronomers call a ring galaxy. Instead of a smooth spiral, its gas and dust seemed to form several overlapping rings. One ring in particular stood out, a massive circle lying about 32,000 light-years, or approximately 9.8 kiloparsecs, from the galaxy's bright core. This spectacular feature earned a poetic nickname, the Ring of Fire. Shrouded in invisible space dust and hidden from ordinary light, this ring glows brilliantly in infrared images, marking one of the most active stellar nurseries in the entire galaxy. Later observations using the National Aeronautics and Space Administration's Spitzer Space Telescope provided an even sharper view. Infrared images showed that Andromeda's spiral arms extend from a central bar stretching far beyond the large outer ring. Yet these arms are not perfectly smooth. They appear fractured and uneven, as if past cosmic encounters had disturbed the galaxy's original design. Closer examinations of the galaxy's inner regions with the same telescope uncovered a smaller ring of dust. Astronomers believe this inner ring formed when the tiny satellite galaxy, Messier 32, collided with Andromeda's disk more than 200 million years ago. Computer models suggest that this collision occurred along Andromeda's polar axis, stripping away more than half of Messier 32's mass. The violent encounter also triggered the formation of the circular rings that now dominate much of Andromeda's structure. The presence of both the large, older outer ring and this newly discovered inner ring, slightly off-centre from the galaxy's heart, strongly supports the idea that Andromeda experienced a nearly head-on crash with its companion, though less dramatic than the event that created the famous Cartwheel Galaxy. Studies of Andromeda's vast outer halo reveal remarkable similarities to the Milky Way. Most of the stars in this halo are old and metal-poor, meaning they contain fewer heavy elements than younger stars, and the abundance of these elements drops the farther the stars are from the galaxy's centre. This resemblance suggests that both Andromeda and the Milky Way grew in similar ways, largely by absorbing smaller galaxies. Astronomers estimate that over the past 12 billion years, each has swallowed between 100 and 200 smaller galaxies. The halos of both galaxies are so enormous that the outermost stars may reach nearly 1/3 of the distance between the Milky Way and Andromeda themselves, a vast invisible bridge of ancient starlight stretching across the cosmos. At the very core of the Andromeda galaxy lies a dense, tightly packed cluster of stars, much like the one found at the centre of our Milky Way. When viewed through a powerful telescope, this bright heart appears as a single shining point surrounded by a soft, glowing halo. In the year 1991, the Hubble Space Telescope captured a detailed image of Andromeda's core, revealing that it actually contains two distinct bright spots. These centres lie about 1.5 parsecs, or roughly 5 light-years apart. The brighter spot, called P1, sits slightly to the side, while the dimmer P2 marks the galaxy's true centre. Within P2 lies an even smaller, compact cluster of stars known as P3, filled with hot, blue-white A-type stars. At its very heart rests Andromeda's supermassive black hole, named Messier 31 star. This colossal black hole is a quiet, low-luminosity active galactic nucleus, feeding slowly on surrounding matter and emitting primarily radio waves and X-rays. Between the years 2004 and 2005, it remained mostly calm, but it flared dramatically between 2006 and 2007, and again in the year 2013. Early estimates in 1993 suggested its mass was between 30 and 50 million times that of our Sun, while later studies in 2005 revised this to between 110 million and 230 million solar masses. The gas and dust swirling around this giant move at incredible speeds of roughly 100 miles per second. Scientists think that Andromeda's unusual double centre might be caused by a disk of stars moving around the main black hole in stretched, or oval paths. In these paths, stars spend more time at their farthest points, creating a patch of light that makes one side look brighter. This oval disk may have formed after two black holes collided a long time ago, sending out waves of gravity that shook and rearranged the nearby stars into their current paths. Inside P2, there is also a small disk of hot A-type stars that shine strongly in blue and ultraviolet light, making P2 look brighter than P1 when seen through certain filters. When this strange double centre was first discovered, some scientists thought the brighter part might be the remains of a small galaxy that Andromeda had swallowed. But this idea is no longer accepted, because such a centre would not have lasted long under the strong pull of Andromeda's main black hole. While it might be possible for P1 to have its own small black hole that helps it stay stable, the way the stars are spread out does not support this. Instead, the twin centres of Andromeda's core show that it has a much more complicated and fascinating past, one shaped by old crashes, gravity movements, and the never-ending pull of the galaxy's main black hole. By the end of the year 1968, scientists still had not found any X-rays coming from the Andromeda galaxy. Then, on the 20th of October in 1970, a high-altitude balloon test set a limit on how strong any X-rays from Andromeda could be. Many years later, the Swift Burst Alert Telescope, during a full-sky survey, finally found strong X-rays coming from a small spot about 6 arc-seconds away from the galaxy's centre. Further study showed that the X-rays with energies above 25 kilo-electron-volts came from a single source called 3X MMJ 00423 2.1 plus 411314. This source turned out to be a pair of objects, a dense, heavy object, either a neutron star or a black hole, pulling in and eating matter from a nearby star and giving off large amounts of energy in the process. Since then, scientists using the European Space Agency's Space Telescope, XMM Newton, have found many more X-ray sources scattered across Andromeda. According to Robin Barnard and his team, these strange objects are likely black holes or neutron stars. As they swallow nearby gas, it becomes so hot, reaching millions of degrees, that it shines brightly in X-rays. The two kinds can be told apart mostly by their weight, with black holes being much heavier. Later, the NuSTAR Space Telescope found 40 of these objects in Andromeda, showing a busy population of small but powerful systems. In the year 2012, scientists saw something even more amazing, a microquasar, a smaller version of a quasar powered by a black hole that gives off strong radio waves. This tiny black hole, found near Andromeda's centre, had about 10 times the mass of our Sun. It was first seen in data from XMM Newton, and later confirmed by NASA's Swift Gamma-Ray Burst mission, the Chandra X-ray Observatory, the Very Large Array, and the Very Long Baseline Array. This was the first time such a microquasar had ever been found, not just in Andromeda, but also outside our own Milky Way. Andromeda also has many globular clusters, round, dense groups of old stars. Around 460 of these clusters belong to the Galaxy. The biggest one, called Male 2, or Globular 1, is brighter than every other globular cluster in the whole local group of galaxies. Holding several million stars, it shines about twice as brightly as Omega Centauri, the brightest cluster in the Milky Way. Interestingly, Male 2 has several generations of stars and is too large and complex for an ordinary cluster, leading scientists to think it might be the leftover core of a small galaxy that Andromeda swallowed long ago. The brightest cluster seen from Earth is called G76, found along the eastern half of Andromeda's southwestern arm. Another large cluster, 037 B327, or Bol 37, found in 2006, was once thought to be even bigger than Male 2, but later research showed it is similar in size and features instead of larger. Unlike the Milky Way's globular clusters, which are all very old, Andromeda's clusters show a wide range of ages. Some are as old as the galaxy itself, while others are much younger, only a few 100 million to about 5 billion years old. In 2005, scientists found a completely new kind of star cluster in Andromeda. These new clusters have hundreds of thousands of stars, like globular clusters in number, but are much bigger, stretching hundreds of light years across. Because of their size, they are also much less dense, with more space between each star. The largest globular cluster in Andromeda, called B023G078, is thought to have a medium-sized black hole at its centre, one that weighs nearly 100,000 times as much as the Sun. In the year 1999, scientists saw an interesting microlensing event in Andromeda, named PA99N2. This event was caused by the bending of light from a faraway red giant star, likely by another star with a mass between 0.02 and 3 6/10 that of the Sun. The data even suggested that this lensing star might have a planet about 6 1/3 times the mass of Jupiter. If proven, it would have been the first planet ever found outside our galaxy, an extragalactic planet. However, later studies showed some strange details in the data, making the finding uncertain. Andromeda, much like the Milky Way, has its own group of smaller companion galaxies, more than 20 dwarf galaxies that orbit it. The best known are Messier 32, M32, and Messier 110, M110. Evidence shows that M32 once passed very close to Andromeda and may once have been a bigger galaxy before Andromeda tore away its outer parts. This event probably caused a burst of star formation in M32's centre that lasted until fairly recently. Messier 110 also seems to be interacting with Andromeda. Scientists have found streams of metal-rich stars in Andromeda's halo that were likely pulled away from these smaller galaxies. M110 has a dark, dusty band that suggests star formation is still happening or happened not long ago, while M32 has younger stars as well. The Triangulum galaxy, another close member of our galactic neighbourhood, floats in space about 750,000 light-years away from the grand Andromeda galaxy. Astronomers are still unsure whether Triangulum is truly a satellite companion of Andromeda or just a nearby neighbour travelling on its own path through space. In the year 2006, astronomers made a surprising and fascinating discovery that captured the imagination of the scientific world. They found that 9 of the smaller galaxies orbiting the Andromeda galaxy seem to line up neatly in a single gigantic plane, stretching straight through the heart of Andromeda itself. This unusual and elegant arrangement suggested that these galaxies might share a connected history. Perhaps they were born together billions of years ago, or maybe they were gradually pulled into their current positions by the enormous gravitational force of Andromeda's massive core. The sight of such a cosmic alignment was like seeing a perfectly choreographed dance of galaxies across the universe. Andromeda itself is a truly majestic spiral galaxy, the largest and most distant neighbour of our own Milky Way. It is slowly but steadily moving toward us at a breathtaking speed of about 110 kilometres, or roughly 68 miles every single second. But when astronomers measure its motion in relation to the Sun, it appears to approach even faster, at around 300 kilometres, or 190 miles per second. This difference exists because our Sun is not standing still. It is also racing through space, orbiting the centre of the Milky Way at a staggering speed of about 225 kilometres, or 140 miles every second. The idea that both our Sun and Andromeda are hurtling through the cosmos in a delicate cosmic ballet is both humbling and thrilling. Because of this movement toward us, Andromeda is one of only about 100 known galaxies whose light is blue-shifted. This means that as the galaxy approaches, its light waves are slightly compressed, giving them a faint bluish tint when observed through powerful telescopes. Despite astronomers measuring its approach with incredible precision, they are still less certain about how Andromeda moves sideways, or tangentially in relation to our Milky Way. Most scientists think that this sideways motion is much slower compared to its forward rush toward us. Early calculations of this sideways motion led astronomers to predict that Andromeda and the Milky Way would collide head-on in approximately 4 billion years. However, more recent and accurate measurements from the Gaia spacecraft have given scientists a clearer understanding of how nearby galaxies within our local group influence one another through gravity. These updated calculations suggest that while Andromeda and the Milky Way may still pass close enough to interact dramatically, the chances of a direct, catastrophic collision are now considered smaller than previously thought. If a cosmic meeting does occur, it would be one of the most awe-inspiring spectacles in the history of the universe. The two enormous spiral galaxies might eventually merge to form a single, vast elliptical galaxy, or perhaps create an immense glowing disk unlike anything astronomers have ever seen. Galactic mergers like this are not uncommon. They happen fairly often in dense clusters of galaxies scattered across the cosmos. But what would happen to our Earth and the solar system during such a cosmic encounter remains uncertain. Some scientists suggest that before the final merger, the immense gravitational forces could fling our solar system out of the Milky Way entirely, sending it drifting alone through the vast dark emptiness between galaxies. Others think it might be drawn into the outer edges of Andromeda itself, continuing our journey through space in a completely new cosmic neighbourhood. From the perspective of our tiny planet, the Andromeda galaxy holds a special place in the night sky. It is one of the most distant objects visible to the naked eye, a soft, misty patch of light hovering gently in the darkness. Only a handful of other galaxies, such as the Triangulum galaxy, also known as M33, and the enormous spiral galaxy M81, which can only be glimpsed by those with exceptionally sharp eyesight under perfectly dark skies, share this rare distinction. Andromeda is located within the constellation that shares its name, which can be found by using the nearby constellations Cassiopeia and Pegasus as guides. Cassiopeia forms a striking W in the night sky, while Pegasus is famous for its large square pattern of stars. For observers in the northern hemisphere, Andromeda is best seen on clear autumn nights, when it rises high above the horizon and glows most brilliantly around midnight in October. As the months pass, it appears earlier in the evening, roughly 2 hours earlier each month. By September, Andromeda can be spotted in the eastern sky during early evening, and by February, it sets in the western sky before midnight. Even those in the southern hemisphere can catch a glimpse of Andromeda between October and December, though it appears lower in the sky and is easiest to observe from regions closer to the equator. With just a pair of binoculars, viewers can see the galaxy's stretched oval shape and its two brightest companion galaxies, M32 and M110. A small amateur telescope can reveal even more marvels: the faint glowing spiral disk of Andromeda, winding lanes of dark cosmic dust, clusters of sparkling stars, and a massive brilliant star cloud known as NGC 206. The Sombrero galaxy sits near the boundary between the constellations Virgo and Corvus, far beyond our own home in space, at a distance of about 31 million light-years from the Milky Way. In other words, the light we see from it today began its journey long before the earliest humans walked the Earth. This galaxy is part of a loose family of galaxies known as the Virgo 2 groups, which stretch outward like a shining trail from the southern edge of the enormous Virgo supercluster. In size, the Sombrero galaxy slightly surpasses our Milky Way. Its wide disk spans roughly between 95,000 and 105,000 light-years from one side to the other. What truly makes it unforgettable, however, is its appearance. At its centre lies a bright, glowing bulge packed with stars. Wrapped around this glowing heart is a thick, dark band of dust that blocks some of the light behind it. From our point of view on Earth, this dark band cuts across the bright centre in just the right way to make the galaxy look like a giant hat with a wide brim. Because of this shape, astronomers gave it the name Sombrero, after the traditional Mexican hat. For many years, early astronomers thought the Sombrero was simply a normal spiral galaxy with a small and faint outer halo. This idea changed when the Spitzer Space Telescope studied the galaxy in infrared light. These observations revealed that the halo surrounding the Sombrero is far larger and heavier than anyone expected. In fact, it looks more like the massive halo usually seen around giant elliptical galaxies. This surprising result blurred the neat categories scientists once used to sort galaxies and made the Sombrero even more mysterious and fascinating. Despite its great distance, the Sombrero galaxy appears fairly bright in the sky, with an apparent brightness of around +8. This means it can be seen using small backyard telescopes under good viewing conditions. Some astronomers even believe it may be the brightest galaxy within a range of about 10 megaparsecs from the Milky Way. Its huge central bulge, powerful supermassive black hole, and dramatic dust lane have made it a favourite target for both professional researchers and skywatching amateurs. The story of how the Sombrero galaxy was discovered reaches back to the late 18th century. On the 11th day of May in the year 1781, the French astronomer Pierre Méchain first spotted the object. A couple of years later, in 1783, he described it in a letter to another astronomer, Johann Bernoulli. This letter was later published in a respected scientific journal of the time. Around that same period, Charles Messier also recorded the object in his personal notes, while compiling his famous list of fuzzy objects in the sky. However, although Messier had seen it, the Sombrero was not officially added to what we now call the Messier catalogue until the year 1921. Meanwhile, in the year 1784, the renowned astronomer William Herschel observed the same galaxy on his own. He noticed a dark stripe cutting across its bright disk, which he described as a dark stratum. Today we understand this feature as the thick dust lane that gives the Sombrero its hat-like look. Many decades later, the link between Méchain's discovery, Herschel's observations, and Messier's notes became clear. In 1921, the French astronomer Camille Flammarion rediscovered Messier's handwritten records and confirmed that the object matched NGC 4594. From that moment on, the galaxy was firmly recognised as Messier 104. One of the most beautiful features of the Sombrero galaxy is its dark, smooth dust ring, which circles the bright central bulge like a shadowy crown. This ring holds most of the galaxy's cold atomic hydrogen gas and dust. Scientists believe it also contains a large amount of cold molecular gas, although further studies are still needed to be certain. Observations in infrared light show that this dusty ring is where most of the galaxy's new stars are being born, making it the main region of ongoing stellar creation. Deep in the core of the Sombrero galaxy lies a special type of central region known as a liner, short for low ionization nuclear emission line region. This means that the gas near the centre is only weakly energized, having lost just a small number of electrons. Astronomers have debated for many years what causes this faint glow. In some galaxies, liners are powered by clusters of young hot stars. In others, they are driven by active galactic nuclei, where enormous amounts of energy are released by matter falling into a supermassive black hole. In the case of the Sombrero, infrared studies show very little new star formation near the centre, but they do confirm the presence of a massive black hole. This strongly suggests that the black hole is responsible for the weak energy coming from the galaxy's core. The Sombrero galaxy also stands out because of its unusually large number of globular clusters. These clusters are ancient, tightly packed balls of stars that formed very early in a galaxy's history. Astronomers estimate that somewhere between 1,200 and 2,000 globular clusters orbit the Sombrero. This is far more than the number found around the Milky Way. The way these clusters are spread out closely follows the light pattern of the galaxy's central bulge, except very close to the core itself. This supports the idea that larger bulges tend to host more globular clusters. Measuring the true distance to the Sombrero galaxy has required several clever techniques. One method compares the brightness of planetary nebulae in the Sombrero with similar objects in our own galaxy, giving a distance of about 29 million light-years. Another method, known as surface brightness fluctuation, looks at how smooth or grainy the galaxy's central light appears. Nearby galaxies look more uneven, while distant ones appear smoother. Using this approach, astronomers found distances ranging from about 30 to 32 million light-years. When these results are combined, the average distance comes out to roughly 29 million light-years. In terms of sheer size and weight, the Sombrero galaxy is truly enormous. Its total mass is estimated to be around 800 billion times the mass of our Sun. It also shines very brightly, with an absolute brightness of about -22 in blue light. Because of this, many astronomers consider it the brightest galaxy within a distance of roughly 33 million light-years from the Milky Way. These measurements became even more precise in the year 2016, when the Hubble Space Telescope studied red giant stars within the galaxy. By measuring their brightness, scientists calculated a distance of about 9.5 megaparsecs, which closely matched earlier estimates and confirmed their accuracy. The Sombrero galaxy lies in a busy region of space filled with many other galaxies arranged in a long, thread-like structure that extends outward from the Virgo cluster. Even so, astronomers are still unsure whether the Sombrero truly belongs to a clear and well-defined galaxy group. Some studies suggest it may be part of a small collection of nearby galaxies, while others argue that it may stand largely alone, or perhaps only be paired with a neighbouring galaxy known as UGCA 287. Adding yet another layer to its mystery, astronomers made a remarkable discovery in the year 2009. They found a tiny ultra-compact dwarf galaxy orbiting the Sombrero. This miniature companion is only about 48 light-years across, yet it contains more than 30 million times the mass of our Sun. The Triangulum galaxy is a lovely spiral galaxy that is about 2,730,000 light-years away from Earth, inside the small group of stars called Triangulum. Astronomers often call it Messier 33 or NGC 598. When measured across its visible width, known as its D25 size, it spans about 18.74 kiloparsecs, or roughly 61,100 light-years across. This makes it the third largest galaxy in our nearby group of galaxies, after the huge Andromeda galaxy and our own Milky Way. Even though it is fairly large, the Triangulum galaxy is actually the second smallest spiral galaxy in the local group, coming just after the Large Magellanic Cloud, which is part of a smaller kind of spiral galaxy known as a Magellanic-type galaxy. Many astronomers believe Triangulum may be a partner or follower of Andromeda, or perhaps it is now drifting back toward Andromeda after being closer in the past. This idea comes from the fact that both galaxies move at similar speeds and appear close together in the sky. Interestingly, Triangulum also has what is known as an H2 nucleus, a central area filled with charged hydrogen gas, where new stars are being born. The galaxy's name comes from its group of stars, Triangulum, which means triangle. Some astronomy books and websites also call it the Pinwheel galaxy, although that name more properly belongs to another galaxy, Messier 101 in the constellation Ursa Major. Still, the nickname Pinwheel Galaxy sometimes appears in telescope software and astronomy websites, showing how easily names can become confused in space research. Under very dark and clear skies, far from city lights, the Triangulum galaxy can sometimes be seen without a telescope. For those lucky enough to spot it, this dim and misty patch of light is the most distant object the human eye can see, almost 1.5 times farther away than the Andromeda galaxy. Unlike stars, which appear as sharp points of light, Triangulum looks like a soft fuzzy glow because it is wide and spread out. How easy it is to see depends on how dark and clear the sky is. In deep rural areas with no light pollution, some people can see it directly, while others may only notice it by looking slightly away from it, a method called averted vision. Because of this, the galaxy is often used as a reference on the Bortle dark sky scale, which rates how dark the night sky is. Although its overall apparent brightness, called its V magnitude, is about 5.72, its true visual brightness is closer to 6.6. This means that only people with very sharp eyesight and excellent sky conditions can see it without a telescope. For most people, even under ideal skies, it is simply too faint to see with the naked eye. The Triangulum galaxy has a long and fascinating history of discovery. It was likely first noticed before the year 1654 by the Italian astronomer Giovanni Battista Hodirna, who described it as a cloudy patch near the constellation Triangulum. More than 100 years later, on the night between August 25th and 26th in 1764, the French astronomer Charles Messier found it again on his own. He listed it as the 33rd object in his famous list of nebulae and star clusters, hence the name Messier 33. Later, the well-known astronomer William Herschel added it to his own list on September 11, 1784, naming it HV17. Herschel also studied several glowing clouds of gas inside Triangulum, called H2 regions, where young stars are forming. One of these, named NGC 604, lies northeast of the galaxy's bright centre and is one of the largest H2 regions known. It stretches about 1,500 light-years across, an enormous area that glows in a way similar to the famous Orion Nebula. Herschel also noted 3 smaller nearby H2 regions, listed as NGC 588, 592, and 595. In the middle of the 19th century, around the year 1850, Lord Rosse was among the first to identify Triangulum as a spiral nebula, noticing its elegant swirling shape. Later, in the early 1920s, astronomers John Charles Duncan and Max Wolf discovered stars within it, whose brightness changes over time, known as variable stars. In 1926, Edwin Hubble studied 35 of these stars, called Cepheid variables, and used them to measure how far away Triangulum is. His work helped show that spiral nebulae like Triangulum were not just clouds of gas inside our Milky Way, but were entire galaxies on their own, huge systems filled with stars. The Triangulum galaxy is believed to contain about 40 billion stars, far fewer than the Milky Way's 400 billion, and tiny compared to Andromeda's trillion stars. Its flat disk holds between 3 and 6 billion times the mass of our Sun, while its gas alone makes up about 3.2 billion solar masses. Altogether, the galaxy's normal matter, known as baryonic matter, may weigh about 10 billion solar masses. When dark matter is added, however, the total mass rises to nearly 50 billion solar masses, within a distance of about 55,000 light-years from its centre. Astronomers have worked carefully to measure exactly how far Triangulum is from us. Most estimates place it between 2,380,000 and 3,070,000 light-years away, with most scientists agreeing on an average distance of about 2,770,000 light-years. This makes it slightly farther away than Andromeda. Triangulum is also about 750,000 light-years from Andromeda, which supports the idea that the two galaxies may be linked by gravity. In the year 2006, astronomers discovered a pair of stars in Triangulum that regularly pass in front of each other, called an eclipsing binary system. By studying how their light changes as they move, scientists were able to determine their sizes, brightness, and exact distance. About 3,070,000 light-years from Earth. This confirmed earlier estimates and became one of the most precise distance measurements ever made for a nearby galaxy. The Triangulum galaxy also sends out a special type of signal known as a water maser, which helps astronomers track how it moves through space. In 2005, scientists using this method found that Triangulum is moving toward the Andromeda galaxy at a speed of about 190 kilometers per second. This supports the idea that it may be orbiting Andromeda or moving back toward it after a close encounter long ago. Further research in the early 21st century revealed a faint stream of hydrogen gas linking the two galaxies, suggesting they may have interacted in the past. Later observations confirmed this connection, showing that their short distance, less than 300 kiloparsecs, or about 1 million light-years, makes such an interaction very likely. Near Triangulum is a small galaxy called the Pisces Dwarf, also known as LGS-3. It lies about 2,022,000 light-years from the Sun and sits roughly halfway between Andromeda and Triangulum. Since it is about 913,000 light-years from each, it could be a small companion of either galaxy. It contains around 26 million solar masses of material and has a central region about 483 light-years wide. Another faint object, called Pisces 7 or Triangulum 3, may also be a small companion of the Triangulum galaxy. In the updated Hubble Sandwich system used to group galaxies created by the French astronomer Gérard de Vaucouleurs, the Triangulum galaxy is marked as type SASCD. Each part of this label tells astronomers something about how the galaxy looks and is built. The letter S means the galaxy has a flat disc-shaped form with gas and dust swirling outward from its bright middle, the classic shape of a spiral galaxy. The letter A shows that its centre does not have a straight bar running through it, unlike SB-type galaxies, which do. The S, added by the American astronomer Alan Sandage, means the spiral arms begin directly from the centre instead of from a ring around it. Finally, the CD at the end shows that the galaxy's arms are loosely wrapped and wide open, giving it a soft and elegant look. The Triangulum galaxy is tilted at an angle of about 54 degrees as seen from Earth. This tilt is useful because it allows astronomers to view its disk and spiral arms clearly, with little blocking from its gas and dust clouds. When scientists closely study the shape of the galaxy's disk, they saw that it bends or curves slightly outward, reaching a distance of about 8 kiloparsecs from the centre, around 26,000 light-years. Although there may be a faint outer layer of stars and gas around it, the Triangulum galaxy does not appear to have a thick, swollen centre, like many other spiral galaxies. What makes the Triangulum galaxy even more interesting is how alone it seems to be. There are no clear signs that it has recently smashed into or merged with other galaxies, and it does not show faint star streams or small nearby companion galaxies like those seen around the Milky Way. It is officially described as an unbarred spiral galaxy, yet closer observations suggest that a weak, short, bar-like shape may exist near its centre. This faint feature reaches out to a distance of about 0.8 kiloparsecs, just over 2,500 light-years, showing that even galaxies without strong bars can still have small bar-like patterns in the galaxy's central region, which covers about 4 arc-minutes across the sky. Something very interesting is taking place. In this area, clouds of atomic gas are changing into molecular gas and giving off strong carbon monoxide signals, a clear sign that molecules are forming quickly. This happens as huge molecular clouds grow thicker from the gas and dust that fill the space between stars. Farther from the centre, the same process continues but much more slowly. Overall, about 1/10 of all the gas in the Triangulum galaxy is molecular gas, which is the main material needed to create new stars. Star formation in the Triangulum galaxy follows a simple rule. The denser the gas in a region, the faster new stars form there. In fact, the speed of star formation per area is higher than in the nearby Andromeda galaxy. For every square parsec of its disk, Triangulum forms stars at an average rate of about 3.4 solar masses per billion years, compared to only about 0.74 in Andromeda. Altogether, the entire galaxy creates about 0.45 solar masses of new stars each year, although astronomers are still unsure whether this rate is staying steady or slowly dropping over time. When scientists examined the chemical makeup of the Triangulum galaxy, they discovered that it seems to be divided into 2 main regions, each with a different past. The inner disk, stretching about 30,000 light-years or 9 kiloparsecs from the centre, shows a normal pattern in its chemistry. The amount of heavy elements slowly decreases as you move outward. Beyond this zone, reaching out to about 82,000 light-years or 25 kiloparsecs, this pattern becomes much flatter. This suggests that the outer disk and the surrounding halo went through a different history of star formation than the inner regions. Many astronomers believe this matches the inside-out model of how galaxies grow. In this model, a galaxy forms its dense inner regions first, where stars quickly use up much of the available gas. Over long periods of time, fresh gas is slowly pulled in from nearby space and settles in the outer regions, starting new waves of star formation later on. Because of this process, stars farther from the centre are usually younger than those closer to the core, telling a calm but beautiful story of how the Triangulum galaxy has slowly expanded outward. By the year 2007, astronomers using the powerful infrared sight of the Spitzer Space Telescope had detected a total of 515 separate sources of 24 micrometer radiation shining within the Triangulum galaxy. These glowing points mark areas rich in dust and gas, often warmed by nearby young stars. The brightest of them are found near the galaxy's centre and spread smoothly along its spiral arms, where many new stars are being born. Many of these glowing clouds are connected to large H2 regions, huge clouds of charged hydrogen, where star formation is actively happening. Some of the most impressive of these are four giant regions known as NGC 588, NGC 592, NGC 595, and NGC 604. Each of these contains massive molecular clouds weighing between 120,000 and 400,000 times the mass of our Sun. The largest and brightest of them, NGC 604, appears to have experienced a powerful burst of star formation about 3 million years ago. This enormous nebula shines with a brightness 45 million times greater than the Sun, making it the second brightest H2 region in the entire local group of galaxies. Other well-known star-forming clouds in the Triangulum galaxy include IC 132, IC 133, and IK 53. The galaxy's northern spiral arm contains four large H2 regions, while its southern arm is filled with groups of young, bright, and extremely hot stars. The Triangulum galaxy also experiences the occasional huge explosion from dying stars. Astronomers estimate that, on average, one supernova occurs about every 147 years, equal to roughly 0.06 type YR and 0.62 type IB, or type 2 explosions per century. By the year 2008, scientists had identified about 100 supernova remains spread across the galaxy, with most of them located in its southern half. This uneven pattern also appears in other features, such as clouds of neutral and charged hydrogen and groups of massive O-type stars. The centre of these features seems to be slightly shifted, by about 2 arc-minutes, toward the southwest. Because the Triangulum galaxy is one of our closest galactic neighbours, the Central Bureau for Astronomical Telegrams continues to monitor it closely for new novae, along with the Andromeda galaxy and Messier 81. Astronomers have also discovered about 54 globular clusters moving within the Triangulum galaxy, although the true number could be as high as 122 or more. These clusters appear to be several billion years younger than those found in the Milky Way, showing that the galaxy has continued forming new clusters until fairly recently. In fact, during the last 100 million years, the rate at which clusters formed seems to have increased, likely due to gas flowing toward the galaxy's centre. The ultraviolet light from its massive stars closely matches that of similar stars in the Large Magellanic Cloud, proving that the Triangulum galaxy is still an active and energetic place where new stars continue to be born. In the same year, 2007, astronomers made yet another thrilling discovery while studying information gathered by the Chandra X-ray Observatory. They found a powerful black hole with a mass about 15.7 times greater than that of our Sun. This object, known as M33X7, belongs to a class called stellar black holes, meaning it formed from the collapse of a massive star. It travels in a tight orbit around a companion star, and every 3.5 days it passes directly in front of that star from our point of view, causing a steady and repeating eclipse. This regular shadowing allowed scientists to study it in great detail, and it still ranks among the largest stellar mass black holes ever discovered. While many famous galaxies, like our own Milky Way or the majestic Andromeda galaxy, hide enormous supermassive black holes at their centres, the Triangulum galaxy is strikingly different. It appears to lack any giant black hole at its core. In most large galaxies, these massive objects sit in the middle, wrapped in a bright swollen cluster of stars known as a bulge. Triangulum, however, does not have this feature. Instead, it is a pure disk galaxy, wide, flat and elegant, with stars spread evenly across its face. Without a dense central bulge, there may have been no place for a supermassive black hole to grow, which could explain why its centre seems unusually peaceful and far less energetic than the blazing hearts of larger galaxies. Closer observation has also revealed that the Triangulum galaxy is not completely isolated in the vastness of space. It is lightly linked to the Andromeda galaxy by faint, almost invisible bridges made of neutral hydrogen gas, along with thin trails of drifting stars. These ghost-like connections are difficult to see, but they speak volumes. They suggest that long ago, possibly sometime between 2 billion and 8 billion years ago, Triangulum and Andromeda may have passed close to one another, brushing past like dancers sharing the same floor before moving apart. Astronomers think this ancient encounter may have been only the first act, and that in roughly 2.5 billion years, the two galaxies could meet again in a far more intense and dramatic collision. By the year 2009, scientists were still deeply divided about what would ultimately happen to the Triangulum galaxy. Some believed that Andromeda's enormous pull of gravity would slowly tear it apart and absorb it, using its rich supply of hydrogen gas to fuel new waves of starbirth. Others thought Triangulum might simply use up its remaining gas over time, growing dimmer and quieter until it faded into a faint, lifeless remnant. There were also more daring ideas. Some researchers suggested that Triangulum could become part of the massive future crash between the Milky Way and Andromeda, merging with both to form a single, giant galaxy. A few even imagined a stranger fate, that Triangulum might collide with the Milky Way first, or be flung completely out of the local group, sent drifting alone into the dark space between galaxy clusters. Then, in the year 2019, a major breakthrough reshaped these theories. Using extremely precise measurements from the Gaia Space Observatory, astronomers uncovered new clues about how Triangulum is moving through space. The data revealed that Triangulum is not calmly circling Andromeda as once thought. Instead, it appears to be falling inward toward it for the very first time. If this is correct, we are witnessing the opening moments of a remarkable cosmic journey. The start of Triangulum's long and complex path toward a future reunion with Andromeda. A slow but powerful dance that will transform both galaxies over billions of years yet to come. The Whirlpool galaxy is a classic example of what astronomers call a grand design spiral, meaning its long curved arms are clear, graceful and neatly shaped, wrapping around the centre like a cosmic pinwheel. At its heart lies a very active core called a Seyfert Type II centre, where a gigantic black hole sits hidden among bright glowing clouds of gas and dust. This galaxy rests in the constellation Canes Venatici, also called the Hunting Dogs, and it holds a special place in astronomy because it was the very first galaxy ever recognised as having a spiral shape. The Whirlpool galaxy is located about 31 million light-years away from Earth, which is roughly 9.5 megaparsecs in distance. From one end to the other, it stretches close to 77,000 light-years across, making it slightly smaller than our own Milky Way galaxy. It is not drifting through space alone. Nearby is a smaller companion galaxy known as NGC 5195. These two galaxies are locked together by gravity, and are slowly pulling on each other, twisting their shapes and stirring up clouds of gas. This slow but powerful cosmic interaction is so striking that, under dark skies, it can even be spotted with simple binoculars, making the Whirlpool a favourite target for skywatchers. Because the Whirlpool and its companion are so close and so clear, astronomers have studied them for many years. By carefully observing this pair, scientists have learned how spiral arms are formed, how gravity allows galaxies to influence one another, and how close encounters and collisions can shape the structure of the universe. For this reason, the Whirlpool system has become one of the most famous and important examples of interacting galaxies. The story of how this galaxy was discovered reaches back more than 2 centuries. On the 13th day of October in the year 1773, the French astronomer Charles Messier noticed this hazy object while searching the sky for things that might be confused with comets. He added it to his growing catalogue of fuzzy sky objects and labelled it Messier 51. Many years later, during the 19th century, an Irish astronomer named William Parsons, also known as the 3rd Earl of Rosse, studied the object using a massive 72-inch reflecting telescope at Birr Castle. What he saw was astonishing for the time. The object clearly showed a spiral pattern. This marked the first time such a shape had ever been seen in the heavens, even though people then did not yet realise that these spiral forms were entire galaxies far beyond our own. It was not until the 20th century that the American astronomer Edwin Hubble finally solved this mystery. By discovering special stars called Cepheid variables within these spiral objects, he was able to measure their enormous distances. His work proved that spiral nebulae were not small clouds inside the Milky Way, but separate galaxies far beyond it. As astronomy advanced further in the middle of the 20th century, radio telescopes allowed scientists to see the Whirlpool in new ways. Radio images confirmed that the Whirlpool galaxy and its smaller partner were truly interacting, connected by invisible bridges of gas and gravity. Today, when astronomers speak of Messier 51, they often mean the entire system of both galaxies together. To make things clearer, the larger galaxy is usually called M51A, While the smaller companion is known as M51b, the Whirlpool lies deep within the constellation Canes Venatici. Skywatchers often locate it by first finding the bright star Alkid, which marks the end of the Big Dipper's handle, and then moving about 3.5 degrees toward the southwest. Because of where it sits in the sky, the Whirlpool never dips below the horizon for people living north of the 43rd parallel, meaning it can be seen all year long from many northern regions. It appears highest and clearest in the sky between November and May. Under dark skies, ordinary binoculars reveal the Whirlpool as a faint misty patch of light. With a small telescope about 10 centimeters across, its two galaxies can be seen as separate shapes. A telescope around 15 centimeters wide begins to show hints of its spiral arms, while larger telescopes of 30 centimeters or more, used under truly dark conditions, reveal bright, sweeping arms filled with glowing regions where new stars are being born. Photographs capture far more detail than the human eye ever could. Long exposure images show delicate clouds and thin streams of material stretching far beyond the visible spiral arms. In the year 1984, astronomers using a special fast detector called an image photon counting system on the Canada-France-Hawaii telescope at Mauna Kea discovered that the Whirlpool's core is actually split into two parts, revealing just how complex and active its center truly is. In January of the year 2005, the Hubble Space Telescope took one of the most detailed images ever made of the Whirlpool galaxy. The picture, built from more than 11,000 by nearly 8,000 pixels, displayed its sweeping arms in stunning detail, showing dark lanes of dust, brilliant clusters of young stars, and glowing clouds of gas scattered throughout. The Whirlpool galaxy is estimated to lie somewhere between 23 and 31 million light-years from Earth. Research published in the year 1991 suggests that it is about 88% the size of the Milky Way and has a total mass of roughly 160 billion times that of the Sun. Scientists believe it is about 400 million years old, which makes it relatively young when compared to many other galaxies. At the very centre of the Whirlpool sits a supermassive black hole. For many years, astronomers thought this black hole was surrounded by a complete ring of dust. Later studies showed that the dust actually blocks and hides part of the black hole, rather than forming a perfect circle around it. From this energetic core, two bright cones of charged gas shoot outward into space, revealing the powerful and restless heart of this magnificent galaxy. The Whirlpool galaxy, also called Messier 51 or NGC 5194, is a large and breathtaking spiral galaxy known for its beautiful shape and detailed pattern. It has two wide and easy-to-see spiral arms that twist in a clockwise direction, although one arm curves slightly out of line. Astronomers believe this unusual shape was created by a close encounter between the Whirlpool galaxy and its smaller companion, NGC 5195. Studies show that this smaller galaxy likely passed through the main disk of the Whirlpool about 500 to 600 million years ago. During that ancient event, NGC 5195 probably came from behind Messier 51, moved through its disk toward our line of sight, and then crossed it again between 50 and 100 million years ago. Today, it appears just behind the Whirlpool galaxy, locked in a slow and dramatic pull caused by gravity. This close encounter between the two galaxies has produced many impressive tidal features, huge streams and clouds of stars and gas stretched out into space by their shared gravitational pull. The largest of these is known as the Northwest Plume, which extends about 43 kiloparsecs, or roughly 140,000 light-years, from the centre of the galaxy. This plume glows faintly, suggesting it came from the Whirlpool galaxy itself. Nearby are two slightly bluer features called the Western Plumes, which are further signs of the ongoing gravitational struggle between these galactic neighbours. In 2015, astronomers discovered two additional features, called the Northeast Plume and the South Plume. These findings confirmed that the interaction between Messier 51 and its companion happened more than once. Computer simulations showing several passes of NGC 5195 through the Whirlpool galaxy closely match what scientists observe today. At the centre of the Whirlpool galaxy, stars are being born faster than normal. Astronomers explain that the speed of this star creation, the number of new stars compared to the amount of gas available, is about 1% similar to the Milky Way. However, this active period of starbirth will not continue forever. It is expected to last for about another 100 million years before slowing down. The spiral arms also shine brightly with young stars, glowing with the light of newly formed suns spreading throughout the galaxy. Over time, the Whirlpool galaxy has also experienced several bright supernova explosions, the violent deaths of massive stars. The first recorded event appeared in 1994 and was named SN 1994I. It was a Type Ike supernova caused by a large star that had already lost most of its outer layers, reaching a brightness of magnitude 12.91. Another explosion occurred in June 2005, when an amateur astronomer named Wolfgang Klur discovered SN 2005 Ceres, a Type II supernova that reached magnitude 14. Later, on the 31st of May in 2011, another Type II supernova called SN 2011-DH was observed shining at magnitude 12.1. It had an unusually blue colour and showed signs of material being thrown outward at very high speed, suggesting the dying star was likely a yellow supergiant rather than a red or blue one. On the 22nd of January in the year 2019, astronomers observed a strange and exciting event in the Whirlpool galaxy. A mysterious burst of light, known as a supernova imposter, appeared and was named AT 2019 ABN. At first, scientists thought it was a normal exploding star, but later they realised it was something even rarer, a luminous red nova. This type of event happens when two stars crash into each other and merge, creating a bright but short-lived glow that slowly fades. The star system responsible had already been seen in infrared images from the Spitzer Space Telescope, but when astronomers looked for it in pictures from the Hubble Space Telescope, they found nothing. They believe the star was hidden behind thick clouds of space dust, making it invisible in normal light. Scientists studying the Whirlpool galaxy have also discovered that it contains a wide variety of molecules, showing that it is more than just a collection of stars. It is also rich in chemistry. Within its wide spiral arms and bright core, astronomers have identified molecules such as hydrogen cyanide, hydrogen isocyanide, aldehyde, and diazenylium, which are also found in star-forming regions of the Milky Way. However, some rare molecules, including isocyanic acid and ethanol, have only been detected within about 1 kiloparsec, or roughly 3,000 light-years, of the galaxy's centre. This suggests that the core of the Whirlpool galaxy has special conditions such as stronger radiation or higher temperatures that allow these unusual chemicals to exist. In September of the year 2020, astronomers using the Chandra X-ray Observatory announced a surprising discovery, a possible planet located outside our galaxy. This remarkable object, called M51 ULS-1b, could be the first known planet ever found beyond the Milky Way. Scientists believe this world orbits a powerful X-ray source, a system where a massive B-type supergiant star is paired with a dense dead object, such as a neutron star or a black hole. The planet itself is thought to be slightly smaller than Saturn, and travels around its host at a very large distance, tens of astronomical units away, far farther than Earth is from the Sun. If confirmed, this discovery would show that planets can form and survive even in distant and extreme parts of the universe. Near the Whirlpool galaxy is its smaller companion, NGC 5195, also known as Messier 51b. This small dwarf galaxy is locked in a gravitational dance with the much larger Whirlpool galaxy. For millions of years, their shared gravity has pulled and twisted their shapes into stunning forms. Both galaxies lie in the constellation called Canes Venatici, about 31 million light-years from Earth. Together they form one of the most famous and closely studied galaxy pairs in the universe, a sight that has amazed astronomers and skywatchers for generations. The Whirlpool galaxy is also the brightest member of a small but important group of galaxies known as the M51 group. This group includes the glowing Sunflower Galaxy, also called Messier 63, along with NGC 5023 and NGC 5229. Scientists think this group may be part of an even larger chain of galaxies stretching across space, possibly connecting to the M101 group and the NGC 5866 group. Centaurus is a striking and puzzling galaxy that lies deep within the constellation of Centaurus. It was first found in the year 1826 by the Scottish astronomer James Dunlop, who made his observation from his home in Parramatta, New South Wales, Australia. Since then, Centaurus A has become one of the most closely examined and intriguing galaxies in the southern sky. Astronomers have long argued about its true identity, whether it should be grouped as a lens-shaped galaxy or as a huge oval-shaped one. Its distance from Earth is thought to be between 11 and 13 million light-years, making it the closest known radio galaxy and also the nearest object of a type called a BL-Lac object. Because of this, its active galactic nucleus, the extremely powerful area at its centre, has been the subject of intense scientific study. It appears as the fifth brightest galaxy visible from Earth, which makes it a popular target for hobby astronomers, although it can only be clearly seen from the southern hemisphere and from low northern regions. At the centre of Centaurus A sits an enormous supermassive black hole with a mass about 55 million times greater than that of our Sun. From this massive core, a stream of particles is blasted outward at speeds close to half the speed of light, releasing huge amounts of energy in both X-ray and radio light. Studies carried out over 10 years have shown that the inner parts of this stream move at incredibly fast speeds, while farther away the stream slams into clouds of gas, producing flashes of X-rays and forming highly energetic particles. The X-ray stream alone stretches thousands of light-years across space, while the radio stream reaches even farther, more than 1 million light-years long, making it one of the largest and most impressive structures ever found in a nearby galaxy. Centaurus A is also known as one of the closest large starburst galaxies going through a powerful period of star creation. Scientists believe this activity was set off by a crash between two galaxies, a large oval-shaped galaxy and a smaller spiral one. Over time, these two galaxies began to blend into one, creating huge clouds of dust and gas and igniting the birth of countless new stars. Such crashes are common between spiral galaxies, but encounters between a spiral and an oval-shaped galaxy are much rarer and still not fully understood, which is why Centaurus A remains such an important object of study. The story of its discovery and exploration stretches across almost 200 years. After Dunlop first noticed it on the 29th of April in 1826, the well-known astronomer John Herschel described it in 1847 as looking like two glowing halves of a cloudy object split apart by a dark strip of dust. Nearly 100 years later, in 1949, John Bolton, Bruce Slee and Gordon Stanley identified it as one of the first galaxies known to give off strong radio signals. In 1954, Walter Bader and Rudolf Minkowski suggested that its strange appearance was caused by a galaxy collision, an idea that later studies have supported. Over the years, many major discoveries followed. In 1970, scientists detected X-rays from the galaxy using a research rocket. In the middle of the 1970s, gamma rays were seen for the first time. In 1979, the Einstein Observatory revealed an X-ray stream coming from the centre, and 10 years later, the Hubble Space Telescope found young blue stars forming along the dark dust strip. In 1999, the Chandra X-ray Observatory detected more than 200 new bright spots of X-ray light, while in 2006, the Spitzer Space Telescope uncovered an unusual four-sided dust shape glowing in infrared light. In 2009, astronomers at the HESS Observatory in Namibia detected powerful gamma rays from Centaurus A, and the next year, the Pierre Auger Observatory confirmed that it also produces some of the highest energy cosmic rays ever measured. In 2016, new information from the Chandra and XMM Newton space telescopes revealed strange bursts of energy that may be linked to an unknown type of black hole or a medium-sized black hole. More recently, the James Webb Space Telescope, using its MIRI-EFRAS instrument, studied the central area of Centaurus A in amazing detail. These sharp images showed fast-moving clouds of electrically charged gas flowing outward at speeds greater than 1,000 km per second. These flows seem to come from a very small area, only about 6 parsecs wide, around 20 light-years, where the galaxy's powerful stream is crashing into nearby material, creating a chaotic and violent environment filled with shocks and radiation. From Earth, Centaurus A looks like an oval-shaped galaxy, crossed by a thick dark strip of dust that nearly cuts it in half. This dramatic look led astronomer Halton Arp to include it in his Atlas of Peculiar Galaxies in 1966 as a clear example of a disturbed galaxy. Its bright central bulge is made mostly of older reddish stars, while its dusty disk still forms new ones. More than 100 star-forming regions have been found there. 2 exploding stars have also been recorded in this galaxy. The first, called Supernova 1986G, was discovered by Robert Evans on the 3rd of May in 1986. It was a Type Ia supernova, created when a white dwarf star pulls in too much material from a nearby companion and erupts in a brilliant nuclear explosion. This event helped astronomers understand that not all Type Ia supernovae behave in exactly the same way. The second, named Supernova 2016 AG, was discovered in February 2016 and was first believed to be a Type II supernova. Later research, however, showed that it more closely matched a Type 1b explosion caused by the collapse of a massive star that had lost its outer hydrogen layer. Another rare event, a bright red nova known as AT2020 NQ, was seen on the 27th of June in 2020, marking the merging of 2 stars within the galaxy. Even more recently, 2 new novae, at 2024, AEQL, and at 2025, NOC, were found in December 2024 and June 2025. The distance to Centaurus A has been measured using several techniques, such as watching Cepheid variable stars and mirror variables, and most estimates now place it at about 3 to 4 million parsecs, or roughly 12 million light-years away. This makes it not only one of the closest and brightest galaxies near us, but also one of the most complex and active, an enormous cosmic testing ground, where astronomers continue to learn how galaxies collide, change, and create new stars across the universe. Centaurus A sits at the centre of one of the 2 main subgroups that form the Centaurus A Messier 83 group, a gathering of nearby galaxies held together by gravity. The other subgroup is centred on Messier 83, also known as the Southern Pinwheel galaxy. Astronomers sometimes describe these 2 subgroups as one large group, while others prefer to see them as 2 separate systems. In reality, the galaxies around Centaurus A and those orbiting Messier 83 are very close to each other in space and seem to move together, showing little or no movement compared to one another. Altogether, the Centaurus A Messier 83 group is part of a much larger collection of galaxies called the Virgo supercluster, the vast galactic region that also includes our own Milky Way. Like many large galaxies, Centaurus A is surrounded by hundreds of globular clusters, ancient, tightly packed groups of stars that circle its outer regions. Interestingly, some of these objects may not be normal clusters at all, but instead the remains of small galaxies that were torn apart by Centaurus A's strong gravity. The most notable example is an object called VHH 8101, which is believed to contain a central black hole about 800,000 times heavier than our Sun, a strong sign that it was once the core of a much larger galaxy. In the month of July in the year 2021, the Event Horizon Telescope, the same global project that captured the first image of a black hole, released a detailed picture of Centaurus A. This image showed a bright stream of material shooting out from the supermassive black hole at the galaxy's centre, a dramatic feature that helps scientists understand how such black holes shape the galaxies around them. Centaurus A lies about 4 degrees north of Omega Centauri, a stunning globular cluster visible to the naked eye. Because Centaurus A shines strongly and covers a fairly large area of the sky, it is a favourite object for amateur astronomers. Even small telescopes or large binoculars reveal its bright central bulge and the thick, dark dust lane that cuts across it. With bigger telescopes, even finer details can be seen: faint arms, glowing clouds, and delicate shapes carved by cosmic forces. Under extremely clear and dark skies, some observers have even claimed that Centaurus A can be seen without any telescope at all, appearing as a faint blur in the constellation of Centaurus. A dwarf galaxy is a small, dim group of stars, much smaller than our Milky Way galaxy. While the Milky Way contains somewhere between 200 billion and 400 billion stars, a dwarf galaxy may have as few as 1,000 to only a few billion. One well-known example is the Large Magellanic Cloud, a nearby partner of the Milky Way that contains more than 30 billion stars. Some astronomers still argue about whether it should be seen as a true dwarf galaxy or a normal galaxy on its own. since it falls between both groups in size and brightness. The formation and activity of dwarf galaxies are greatly shaped by the pull of much larger galaxies near them. Astronomers have discovered that there are many kinds of dwarf galaxies, and they are usually grouped by their shapes and the substances they contain. Some are smooth and round, while others look uneven and spread out. One common idea suggests that galaxies, including dwarf ones, formed along with large amounts of mysterious dark matter, or from clouds of gas that already held small amounts of heavy elements, which astronomers call metals. But a finding made by the National Aeronautics and Space Administration's Galaxy Evolution Explorer spacecraft revealed something different. Some dwarf galaxies are actually forming from gas that has very little metal in it. These newly forming galaxies were found inside a huge ring of hydrogen and helium called the Leo ring, which circles two massive galaxies in the constellation of Leo. Because they are so small and light, dwarf galaxies often become victims of the strong gravity of nearby spiral galaxies. As they are pulled closer, their stars can be stretched into long glowing paths known as stellar streams, and over time they may be completely ripped apart and absorbed, joining with their larger neighbours. In our own nearby area of space, called the local group, there are many dwarf galaxies moving around larger ones such as the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. In the year 2007, astronomers suggested that some of these dwarfs may have formed from powerful pulling forces, called tidal forces, that happened when the Milky Way and Andromeda were still taking shape. These so-called tidal dwarf galaxies appear when two galaxies crash together, dragging streams of stars, gas, and even the unseen clouds of dark matter away from each other to create new, smaller galaxies. Some dwarf galaxies may be much older than scientists once thought. A study released in the year 2018 suggested that a few nearby dwarf galaxies formed very early in the history of the universe, during the mysterious Dark Ages, less than 1 billion years after the Big Bang itself. Today, astronomers have found more than 20 dwarf galaxies circling the Milky Way. One of the most fascinating discoveries is that the giant globular star cluster known as Omega Centauri may actually be the remaining centre of a dwarf galaxy that was consumed by the Milky Way long ago. At its core, scientists believe, sits a hidden black hole. Among the many types of dwarf galaxies, one especially eye-catching kind is the Blue Compact Dwarf Galaxy, often shortened to Blue Compact Dwarf or BCD Galaxy. These are small galaxies filled with large groups of young, massive and extremely hot stars. Because these stars shine so strongly in blue and white light, the whole galaxy takes on a blue glow. Blue compact dwarf galaxies often have uneven or misshapen forms because they are made up of separate clusters instead of one smooth disk. They are also very active, constantly using gas to create new stars, which leads to strong bursts of energy and fast change inside them. Over time, as their gas cools and new generations of stars are born, their look slowly changes. Nearby examples of these galaxies include NGC 1705, NGC 2915, NGC 3353, and UGC-A 281. Another group of small galaxies is known as ultra-faint dwarf galaxies, or ultra-faint dwarfs. These are the faintest galaxies known in the entire universe, containing only a few hundred to about 100,000 stars. Although they may look somewhat like globular clusters, they are very different inside. Ultra-faint dwarfs are packed with dark matter and spread across much larger areas of space. They were first found in the year 2005 thanks to detailed digital sky searches such as the Sloan Digital Sky Survey. Because ultra-faint dwarfs are ruled by dark matter, astronomers believe they may hold valuable clues about what the universe was like shortly after it began. All those discovered so far seem to be extremely ancient, having formed only a few million years after the Big Bang, long before the universe's first light appeared during the era of Orionization. Some scientists have even suggested that there could be a younger group of ultra-faint dwarfs that formed much later, but none have been observed yet. There is also a special group of dwarf galaxies called ultra-compact dwarfs, or ultra-compact dwarfs. These were discovered in the early years of the 21st century and are among the most tightly packed star systems known. A typical ultra-compact dwarf is only about 200 light-years wide, but can contain nearly 100 million stars squeezed closely together. Many astronomers think these dense objects are actually the stripped-down centres of larger dwarf galaxies, whose outer stars and gas were pulled away as they moved through crowded galaxy clusters. Ultra-compact dwarfs have been found in the Virgo cluster, the Fornax cluster, Hubble 1689, and the Coma cluster. One well-known example, M60 Ultra-Compact Dwarf 1, is located about 54 million light-years away. It holds around 200 million times the mass of our Sun packed into a space only 160 light-years across. The stars at its centre are 25 times more crowded than those in the part of the Milky Way where our Sun sits. Another, called M59 Ultra-Compact Dwarf 3, is similar in size but shines about 40% brighter, making it the second most tightly packed galaxy ever known. Some ultra-compact dwarfs in the Virgo cluster even seem to contain huge black holes at their centres, making up more than 1/10 of their total mass, a sign that these small galaxies may once have been much larger cosmic systems in the distant past. Bodes Galaxy is a beautiful spiral galaxy located about 12 million light-years away in the constellation of Ursa Major, the Great Bear. It is a grand design spiral, which means its arms are easy to see and perfectly shaped, giving it a smooth and orderly look. Across its bright disk, the galaxy stretches roughly 29.5 kiloparsecs, which is about 96,000 light-years, almost the same size as our Milky Way. Because Messier 81 is fairly close to our galaxy and shines brightly in the sky, astronomers around the world have studied it a lot. Its centre has a very strong and active core, which contains a huge black hole weighing around 70 million times the mass of our Sun. This giant black hole makes the centre of the galaxy shine with intense energy, which can be seen in many types of light. Both professional and amateur astronomers often watch Messier 81, not just because it is beautiful, but also because its brightness makes it easy to see, even with small telescopes. In late February of the year 2022, scientists made an exciting discovery. They found that Messier 81 might be the source of a strange cosmic signal called a fast radio burst, specifically FB202001200E. These bursts are strong flashes of radio waves that last only a few milliseconds, yet they release as much energy as the Sun does in several days. Messier 81 was first found on the 31st of December in the year 1774 by the German astronomer Johann Elert Bode. Because of this, the galaxy is often called Bodes Galaxy. A few years later, in 1779, French astronomers Pierre Méchain and Charles Messier saw it again, and added it to Messier's famous list of space objects. From Earth, the galaxy can be found about 10 degrees northwest of the bright star Alpha Ursae Majoris, also called Dubhe. It is part of a small group of galaxies called the Messier 81 group, which has several galaxies close together in the same part of space. Because it is so far away, Messier 81 cannot be seen with the naked eye except under very dark skies and by very experienced observers. But with binoculars or a small telescope, both Messier 81 and its neighbour galaxy, Messier 82, can be seen together, a beautiful view for stargazers. To see details in its spiral arms, a telescope with a diameter of at least 8 inches or about 20 centimetres is usually needed. The best time to see this galaxy is during April, when it rises high in the night sky. Much of the galaxy's light in the infrared comes from space dust. This dust is mostly found in the spiral arms, where new stars are forming. The hot, short-lived blue stars in these areas shine very brightly, heating the surrounding dust and making it glow in infrared light. Astronomers think that Messier 81 has around 210 globular clusters, old, tightly packed groups of stars that orbit the galaxy's centre like sparkling jewels. Only one supernova has ever been seen in this galaxy. It was called Supernova 1993J, discovered on the 28th of March in the year 1993 by the Spanish astronomer F. Garcia. At its brightest, it became one of the most visible supernovae of the 20th century, reaching a magnitude of about 10.7. Its behaviour was unusual. It started as a normal Type II supernova, showing strong hydrogen in its light, but over time the hydrogen faded and helium became stronger. This made astronomers classify it as a Type IIb supernova, a stage between Type II and Type 1b explosions. These results suggested that some Type 1b and Type 1c supernovae might also come from the deaths of giant stars like Type II supernovae. The light from supernova 1993J also helped scientists measure the distance to Messier 81 at about 8.5 million light-years. The Central Bureau for Astronomical Telegrams still tracks new stars that appear in Messier 81, as well as in nearby galaxies like Messier 31 and Messier 33. At the galaxy's centre is its huge supermassive black hole, about 70 million times heavier than the Sun. This black hole is active, surrounded by a glowing disk of falling material, and even sending out a one-sided stream of high-speed particles into space. Some studies suggest there might be a smaller black hole orbiting the main one every 30 years, with a mass about 1/10 of the larger black hole. Messier 81 is the biggest galaxy in its group, which has about 34 members in total. About 12 million light-years from Earth, this group and our local group, which has the Milky Way, Andromeda and Triangulum, are considered close neighbours in the huge Virgo supercluster. Interactions between Messier 81, Messier 82 and another nearby galaxy called NGC 3077 have caused big effects. Their strong gravity has pulled huge amounts of hydrogen gas from each galaxy, creating long streams of glowing gas in space. These interactions have also pushed gas toward the centres of Messier 82 and NGC 3077, triggering strong waves of star formation called starbursts. The Pinwheel galaxy is about 21 million light-years away from Earth, around 6.4 megaparsecs, in the constellation of Ursa Major, the Great Bear. This amazing galaxy is seen face-on, which means we look straight at its wide spiral disk that turns counterclockwise in space. The galaxy was first spotted in the year 1781 by the French astronomer Pierre Messier. Later that same year, he told his friend and fellow astronomer Charles Messier, who checked its position and added it to his famous Messier catalogue as one of the last entries. More than 200 years later, on the 28th of February in the year 2006, NASA and the European Space Agency released a stunningly detailed picture of the Pinwheel galaxy. This photo, made by combining 51 separate shots with a few extra ground-based pictures, became the largest and most detailed image of any galaxy ever taken by the Hubble Space Telescope at that time. When Pierre Messier first saw the galaxy, he described it as a cloud without stars, very faint and quite large, about 6 to 7 arc-minutes across, between the left hand of Bodes and the tail of the Great Bear. It's hard to see when one shines light on the grating wires. In the year 1784, the famous astronomer William Herschel also studied the galaxy. Using telescopes with mirrors 7, 10 and 20 feet long, he wrote that it looked like a spotted kind of cloud that he thought could one day be seen as individual stars with better tools. His notes hinted at the true nature of galaxies long before we really knew what they were. Later, in the second half of the 19th century, Lord Rosse used his huge 72-inch Newtonian telescope to study the same galaxy. He was the first to make detailed drawings showing its amazing spiral shape, an important step in realizing that galaxies were not just faint clouds, but huge systems of stars on their own. Today, the Pinwheel galaxy can be seen even with binoculars or a small telescope, though its delicate spiral arms are best seen with a large telescope, under very dark skies, and with a low-power eyepiece. This galaxy is truly huge. Its disk stretches across about 252,000 light-years, almost 3 times the width of our Milky Way, which is around 87,400 light-years across. The Pinwheel galaxy has nearly 1 trillion stars, with a disk mass about 100 billion times the mass of our Sun. At its centre is a smaller bulge containing about 3 billion solar masses. In size and structure, it can be compared to the Great Andromeda Galaxy. The galaxy has many bright areas called H2 regions, where new stars are formed. These areas are inside giant clouds of dense hydrogen gas that collapse under their own gravity. The strong light from young, hot stars makes the gas glow, creating pink and red clouds that light up the galaxy's spiral arms. In 1990, astronomers listed 1,264 such regions in Messier 101, 3 of them, NGC 5461, NGC 5462, and NGC 5471, are so bright and large that they were added separately to the new general catalogue. Interestingly, the Pinwheel galaxy is not perfectly even. it shows signs of being pulled and stretched by the gravity of nearby smaller galaxies. These interactions squeeze its hydrogen gas, triggering strong bursts of star formation that can even be seen in ultraviolet light. In the year 2001, astronomers using the Chandra X-ray Observatory found a strong X-ray source in the galaxy, called P98. It was found to be an ultra-bright X-ray source, brighter than any single star but not as bright as a whole galaxy, and was later called M101 ULX1. Later observations by the Hubble Space Telescope and XMM Newton in 2005 showed that it was an X-ray binary system. This means it was a pair of objects, one probably a black hole, pulling material from a companion star. Surprisingly, the black hole in this system had only about 20 to 30 times the mass of our Sun, but it was pulling in material much faster than expected. The Pinwheel galaxy also has around 150 globular clusters, about the same number as in our Milky Way. Around it are 6 notable companion galaxies: NGC 5204, NGC 5004, 174, NGC 5004, 177, NGC 5585, UGC 8837, and UGC 9405. The gravity between the Pinwheel galaxy and these smaller galaxies may have shaped its grand, sweeping spiral design. Together, these galaxies form what astronomers call the 101 group, a small, graceful family of galaxies floating through space, held together by gravity and time.